Okay, hi everyone. So this is day 3 of the Clinician Engineer Hub virtual conference. Like I always say on every day, that we are bringing you the best experts in academia and industry across healthcare and engineering. So we're starting day 3 with another fantastic global expert. Live from Cambridge in the United Kingdom, we have Professor George Malliaras, royalty in terms of engineering, Prince Philip Professor of Technology, and has done massive amounts of work in terms of bioelectronics, the brain-machine interface. We heard from Professor Boyden, the work he was doing in that regard. So we're now going to get Professor George's perspective, and I'm sure it's going to be absolutely fantastic. So I will ask you, Professor George, to share your screen, and then we'll be good to go.
Yeah, let me start the beginning. Can you see my screen now?
We can see it, yes, fantastic.
Great, and how about now? My cursor, can you see my cursor?
Can see your cursor nicely, electronics on the brain, and we can hear you.
Thank you. Thank you very much, Neil. I'm impressed, very much impressed by the program you put together. It's exceptional. I've been learning a lot, and it's a great pleasure and a privilege to be part of it. So, hi everyone. We're gonna have a 30-minute or so discussion about the merits of putting electronics on the brain. And let me start by the motivation for this work, which stems from the fact that the leading cause of disability worldwide is neurological disorders. Over 276 million years are lost to stroke, migraine, dementias, epilepsies, and other neurological disorders. And this is a call to arms. What can we scientists and engineers do about this? This is a sobering observation that comes from the pharmaceutical industry. It is called Irum's law, which is Moore's law spelled backwards. Moore's law describes an accelerating trend where electronics becomes more performant and cheaper every year. It's quite the opposite in drug discovery. It gets slower and becomes more expensive to the tune of over $1 billion currently to develop a single drug. So this is not going to solve the neurological disorders issue. The answer has to come from somewhere else. And this somewhere else is a very exciting and emerging field, which is called bioelectronic medicine. And it involves implanting electrodes in the brain or other parts of the nervous system. Here in this demonstration, it's implanted in the subthalamic nucleus. And through constant electrical stimulation, you can alleviate symptoms of motor disorders such as dystonia, Parkinson's, tremor. You can reduce the frequency of seizures in epilepsy. And even recently, there were powerful demonstrations in neuropsychiatric disorders such as obsessive compulsive disorder and depression, as well as interest in applying these techniques to combat obesity. So very exciting, as this demonstration shows here. You go from being unable to hold a glass of water to being able to function almost normally, the tremor almost gone with a flick of a switch. And this is a trend that has been accelerating. So bioelectronic medicine as a field started back in the late 50s, early 60s, with the first implantation of a pacemaker, a device that currently is being implanted to the tune of 600,000 implants per year. A decade later, we had cochlear implants for hearing. A few years later, spinal cord stimulation for pain. Then the vagus nerve became a very important target for epilepsy and some other conditions. Some other peripheral nerves for bladder control. Then the brain in the early 2000s became a major target for bioelectronic medicine with deep brain stimulation for Parkinson's and neuropsychiatric disorders. A couple of other positions in the body, and more recently, this is a very interesting development, is the use of electrical stimulation to address disorders beyond the neurological spectrum, including autoimmune diseases, including things such as diabetes, Crohn's disease. So an ever-expanding spectrum. Very, very exciting news. And the trend really is accelerating. If you look into the number of devices that are being approved, number of devices that are on the pipeline, it's accelerating. Very good news. So what's the catch? What are the limitations? First and foremost, we do not understand how the brain works. And here I echo the comments of Ed Boyden. He mentioned the exact same thing as a key limitation for the technologies he's developing. And rightly so. The human brain is a very complex machine consisting of over 80 billion neurons. And although we understand in a quantitative fashion how a neuron fires an action potential and how that action potential propagates down the axon, and it arrives at the synapse, and it can either inhibit or excite the postsynaptic neuron, we do not understand how we go from that to behavior. And one way you could try to address this problem, and this ties into clinical work that is done on people, on volunteers who are about to do surgery for epilepsy. You have electrodes in different configurations, and you can study the brain and try to understand how neuronal activity leads to behavior. The three configurations that are used in the clinic are electroencephalography, that involves scalp electrodes. This is the least invasive technique. At the other end, you have stereotaxic electroencephalography, where you use penetrating probes that penetrate into the brain's parenchyma. Obviously highly invasive, but here, if the contacts, if the electrodes are small, you can capture single neuronal activities. While here, because you're about 1 centimeter away from the brain, you only capture very average information. Between the two lies electrocorticography, where you would do a craniotomy, expose the surface of the brain, and place an array of electrodes here. This was believed to be intermediate in terms of spatial resolution. It was believed that it couldn't catch single neuronal activity, but it would catch more activities at higher spatial resolution than surface EEG. And certainly it's intermediate in terms of invasiveness. You don't penetrate the brain, so it's not as invasive as stereotaxic electroencephalography. Another thing we do not understand is how do we go from, how do we get changes of behavior when you neuromodulate? So what happens when you inject current with this electrode? You know what happens at the neuronal level, but how does that translate to changes in behavior? These limitations come hand in hand with technology limitations. The signals are small, especially if you try to capture them at the surface of the brain or on the skull. And the environment is hostile to electronics. When you penetrate the brain with a probe, this is bad both for the brain and for the probe. Bioelectronic medicine involves configurations that are highly invasive, and often multiple surgeries are required in order to replace batteries, often contacts. So we urgently need new and better technologies to address these limitations, understand better the brain, and hopefully enable bioelectronic medicine to reach patients at scale. So what I want to, with this as an introduction, what I wanted to do today is show you 3 examples of research. The first one will appeal to those of you who like materials research, and I'll show you how a concept in materials research translates to better communication between brain and electronics. The second is I will talk about a phenomenon which is called electrophoresis, and it allows you to precisely deliver drug in the brain. And finally, I'll show you some recent work where we make devices that change shape, and as such, they can decrease the invasiveness of neurosurgery. So another way to frame bioelectronics is as the interfacing between living systems and microelectronics. And you notice that there are different properties in these two worlds. Here, tissues are mostly soft and squishy, certainly the brain is, while electronics, as we know them in the traditional form, are made out of mechanically hard materials. The communication of components in the world, the living world, is complex and often not very well understood. So the way neurons talk to each other, the way tissues communicate, organs communicate, can be very complex. While here, these two components communicate with each other by exchanging an electron flux, something we understand in a quantitative fashion. Biological systems are dynamic, while electronics are static. They spend their life in the same form factor they've been fabricated in. So in order to do better bioelectronics, what we need to do is make electronics that have properties that are similar to those of living systems. Now, in the past decade, there has been tremendous progress in bridging the mechanical properties mismatch. By making electronics very thin, you can make them conformal to organs in a way that they do not provide any mechanical load. They become flexible, they can even become stretchable with a little bit of extra engineering. So the mechanical properties mismatch has largely been addressed. And today, a lot of action takes place at addressing the communications gap. How can we teach electronics foreign languages so that they can talk to biology in an efficient way and in a bi-directional way, so we can get information from biology to electronics and vice versa, trigger biological phenomena through electrical actuation. So I'll talk about this today. And this is in the context of epilepsy, which is a disease that affects a large part of the world population. It's characterized by recurrent seizures, and about 30% of the patients are resistant to drugs. In cases of drug resistance and severe forms of epilepsy, then resection surgery becomes an option where the patient will come in the hospital, get implanted, excuse me, with electrodes at different parts of the brain to localize the part of the brain that gives rise to seizures. And this is assessed by carrying out recordings from all these electrodes in the brain. So here's a seizure. And then what the clinicians try to do is to backtrack this data and figure out which part of the brain gave rise to the early activity that then manifested itself as a seizure. So key challenges here is to improve the performance of the recording devices so that we can catch these recordings with as high fidelity as possible. And especially, can we catch them without having to penetrate the brain? So to an engineer, this becomes a problem of coupling ionic carriers in an electrolyte. So this would be the sodium, potassium, chlorine ions that exist in the cerebrospinal fluid and are put to motion due to the firing of neurons in the brain. So can you couple these carriers with charge carriers inside your electrode material? And to couple well, they need to be close to each other. If you look at silicon, which is the king of electronic materials, typically it has an oxide or a nitride that separates the bulk of the semiconductor with the electrolyte. So the coupling between ionic and electronic carriers is very inefficient. That's why a lot of people use either platinum or gold electrodes to perform these recordings, because these are electronic materials that have no barrier layer, and you can have close proximity between ions in the electrolyte and electronic charges in your electrode. But even in this configuration, the coupling between the two carriers, the communication between biology, ions, and electrons, is very weak. If you use materials such as this one, which is called P.PSS, and I'm not going to go to the details of the chemical structure, just consider this a material that has a structure akin to a plate of pasta. So it consists of chains through which electronic charges can move, but there is space between the chains, so ions from an electrolyte can penetrate into the bulk of this structure. And as such, they can couple in the whole volume of the material with electronic charges. So in this case, you have coupling between electronics and biology that is much, much stronger. And that allows you to make state-of-the-art devices, or even make devices that have novel characteristics. For example, you can time reverse this process and use your electronic material as a source of ions to the brain and effectuate drug delivery in this fashion. I'll talk about this a bit later. So a manifestation of this phenomenon is a capacitance that depends on the volume of the electrode. While in a typical electrode such as platinum or gold, the capacitance only depends on the area of the electrode. Here we depend also on the thickness of the electrode. By making your layer thicker, you couple more strongly biology and electronics. This means that you can take a layer of this magical material, P.PSS, that is just 130 nanometers thick, very thin layer. And that will increase the coupling of ionics and electronics 2 orders of magnitude compared to a flat metal film of the same area. This means now that you can make your electrode 2 orders of magnitude smaller and still be able to record with the same fidelity as a much larger metal electrode. So you just gained in spatial resolution. This is how this manifests itself. We can make very small metal electrodes. On their own, they're not able to record any neural activity because they just don't couple very well to the brain. But if we put 100 nanometers thick film of this conducting polymer on them, then they begin to record, and they record with high fidelity. So these electrodes are put on a very flexible plastic substrate, and as such, they become conformal to radio of curvatures that are compatible with the brain, the topography of the brain. So this is a device shown on an orchid leaf, and it really provides no mechanical loading. It's very thin. You cannot feel it between your fingers. And interestingly, when this was placed on the cortex of a rat, you could record single neuron signals. So without penetrating the brain, it can capture single neuron activity from underlying cells in the cortex, and can, because it doesn't penetrate the brain, it doesn't disturb the neural environment around these neurons, you can latch onto a neuron and follow it for a long time. Now, this was a compelling advantage compared to the state of the art. And this device was translated to the clinic in record time. And it's now used in several hospitals in the US to do intraoperative recordings in humans with exceptionally high spatial resolution. So it would capture the average so-called local field potentials that consist of spatiotemporal summations of many neurons, but also captures this single neuron signals from neurons of layer 3 of the cortex, pyramidal neurons in layer 3 of the cortex. So this was a couple of years ago already. We are currently making these devices denser so that we can capture the same neuron now from multiple electrodes and try to understand a bit better about the connectivity of neurons in the cortex. And also making them transparent so that we can couple powerful electrophysiology with powerful optical microscopy. This is a demonstration of super resolution microscopy performed through one of these electrodes. So far, I showed you how by using a material which is a so-called mixed conductor where ions and electrons can coexist, you can couple better the world of electronics and biology and achieve high spatial resolution recordings of brain activity. Now we're going to go for the opposite. We're going to use these materials to source ions in the brain. And this is again in the context of epilepsy, where, as I mentioned earlier, anti-epileptic drugs fail to work for about 30% of patients. And when epilepsy is severe, then resective surgery becomes the next option. However, the resection of the epileptogenic zone is not always possible because it may overlap with a high functionality area, and then the cost-benefit analysis just doesn't work for that patient. In these cases, we advocate an implantable device in the epileptogenic zone that effectuates localized delivery of drug when and where is needed. Now, such localized delivery behind the blood-brain barrier is being explored in the context of brain cancer, where post-resection you want to deliver locally chemotherapy in order to kill the remaining cancer cells. And there are different ways of doing this by using, for example, biomaterials or devices that leach out some drug, or by using a catheter and effectuating convection-enhanced delivery, so supplying a solution of the drug locally. There are multiple reasons why none of these techniques would work in epilepsy. Those are not meant for chronic use, while the convection-enhanced delivery applies a lot of pressure locally and can cause neurological deficits, pressure-reduced edemas, and suffers from other limitations. So here, new technology is needed. And we were very excited when about a decade ago, we saw this work from a Swedish group where they use a mixed conductor, P.PSS, the material I mentioned earlier, to bridge two reservoirs of electrolyte. And by applying a potential, they were able to take ions from one electrolyte and move them to the other. And the interesting thing in this device is that it does so. It can deliver an ion from one reservoir to the other in a solvent-free fashion. So it's only the ion that moves through the device and gets delivered, and not the solvent. And as such, it is very much advantageous to convection-enhanced delivery because it doesn't cause a pressure increase at the target reservoir. So the Swedes made an in vivo device and demonstrated that you can regulate hearing in a guinea pig model by supplying acetylcholine. The way this device works is it uses a so-called ion exchange membrane to separate a source where your drug exists in solution in an ionic form from the target, which would be the brain in our application. And by applying a potential, you can get your drug ion to go through the membrane and into the brain, while the membrane has immobilized charge of the opposite charge, the opposite nature, so as the opposite sign. So the transfer of ions from the brain into the device is blocked by that layer. This is how a device looks for rodents. you have a U-shaped microfluidic channel that brings in the drug solution into the brain. So you start from outside the brain, you go into the brain, and here there are holes that are capped with this ion exchange membrane. And by applying a potential, you can get just the drug to cross this membrane and be secreted into the brain, and not the solvent. The solution just gets depleted, and the solvent returns and comes out of the brain. And you can also sensorize the device. You can add electrodes or other sensors to monitor the process. So with this concept, we're able to, by just applying half a volt, to increase the GABA. We use GABA here as the drug of choice, is a inhibitory neurotransmitter, which works very well for this purpose. So by just applying half a volt, we can increase local concentration by several orders of magnitude. And this was validated in a rodent model of epilepsy, where we inject 4-AP locally to create the focal area of a model for focal epilepsy. And in panel A, we have the device implanted but switched off. So when we kindle the seizure, it takes a little bit of time, and here comes the seizure, manifests itself. In panel B, we do the same thing. Here comes the seizure, and then we turn the device on, and we start puffing GABA, and the seizure just goes away. These spikes that you see here are because of an electrical pickup, an artifact. Every time we pump, we apply a voltage pulse to give a puff of GABA, we pick this up with our sensitive recording system, but the seizure is gone. And here is an experiment that shows prevention, where we would turn the pump on, we would try to kindle a seizure, and the seizure just will not materialize itself. And if you go to the paper, you'll see the continuation of this data, where after we stop pumping, then you can kindle a seizure and it will materialize itself. So this is very promising, because it shows that you can not only stop, but also prevent a seizure from happening through localized delivery of inhibitory neurotransmitter that is innate to the body. So then this gets you dreaming. What else can I do? And there is no thing such as one device that fits all scenarios. If you think about brain tumors, the requirements for treatment are very different. For epilepsy, you're looking at an implantable device for the life of a patient. For a brain tumor, you're thinking of weeks of delivering chemotherapy and then removing the device. Target volumes, epileptogenic zones tend to be very small. Tumors can be as large as oranges. So you're looking at 2 centimeter size voxels. And if you look into the physics of this device, this is something that we spend a lot of time on. Here are 3 different parameters. Never mind what they are. Yellow means optimized, blue means not optimized. You see that they're optimized at different spaces of parameters that we explored. And that again means that you cannot make a device that is optimized for every scenario. You have to go and engineer the device differently. So for the case of brain tumors, the device looks very different than that for epilepsy, but it can address large voxels as required for the case of cancer. So this is EPSRC funded research. It's a big center at Cambridge, and we're looking forward to getting this to patients at scale within a time frame of a couple of years. So last thing I want to mention, the last few minutes of my talk, is a device that changes shape and can decrease the invasiveness of neural surgery. This is the placement of a cortical grid on a patient, and you see that it requires a large craniotomy, dura to be removed. It's quite a major procedure. So we were inspired by demonstrations such as this one shown here, where you use pneumatic actuation to make soft objects move. And we coupled these concepts with flexible electronics to make devices that can either expand or unroll. There is a whole range of motion that is possible here. So this is one example. This is a paddle electrode of the same dimensions as the one used to treat pain, neuropathic pain. This is implanted in the spinal cord. And to implant this, you require a laminectomy, which is quite invasive procedure. This particular implant can be rolled into a needle shape, and through a 2E needle, you can implant this using a spinal puncture. And it's a much simpler procedure. And then once it's in, then you can pneumatically activate it as shown here, and it will open up. And we see this in cadavers. We're running the final cadaveric session actually today. This is the same device with some tracker, radio pack tracker at the edges, and you see how it unrolls. And exploring also other configurations, such as this one shown here. This is on a brain, again, of a human cadaver. And the device is implanted through a small burr hole and then expanded to 2 centimeters. So we hope that these devices will change the invasiveness of neural surgery. You'll be able to place a small object that will then open up and cover a large area. So with that, I hope I gave you a feeling for how implantable electronics might change our understanding of the brain and help address some of its pathologies. I talked about mixed conductor materials that enable high resolution cortical electrodes. This is something that's already translated to the clinic. Talked about electrophoretic delivery that is dry. It means that it delivers only the drug without the solvent. It can achieve excellent spatiotemporal resolution. I didn't talk much about this, but it can stop or prevent seizures in animal model. This is now on its way slowly. It's a long journey to the clinic, but it's on its way. And we're very excited about this, looking into implants that change shape to minimize invasiveness of neural surgery. Here we just got ethics permission to try this on dog patients at the veterinary school, and hopefully one day in humans. So let me thank my group, collaborators at Cambridge, other collaborators outside, funding agencies. Without funding, ideas without funding are cannot be realized. So it's extremely kind of this councils to support our research. Thank you, Neil, for having me. I'm ready for questions.
Absolutely. That was, again, mind-blowing. You're covering every element of neurology, and it's insane the amount of work that you've been doing. We have Lady Catherine here from Cleveland, actually. She's going to be leading the questions. So Lady Catherine, do you have any questions at all?
Yes, so first I'd like to thank Dr. Malliaras, because there's, I'm a physician, and definitely I could see how all this technology could be applied on the patients and definitely make a very big difference. One of the questions that I had, I work mostly on the gastrointestinal area. So one of the questions I had for you is, and you mentioned primarily its role in Crohn's disease. So my question for you is, what kind of role would have bioelectronics in Crohn's disease, and would it be more for diagnostic purposes, treatment delivery? What would be the role in that area?
So this is a super exciting topic. As you know, the gut-brain axis is extremely important today, and how the gut microbiome affects the brain is also an exceptionally vibrant area of research today. My wife, actually, who's also an academic, works on that. She makes models of the gut-brain axis that include the microbiome. So we have lots of discussions on this exact topic at the dinner table. What is happening in bioelectronics today is people look at stimulation of different nerves that innervate different organs close to the point of innervation, hoping to be able to bring the organ back into health in case of disease. And to do this, you need to understand the neural language. You need to understand exactly what signals the neuron sends to the organ and what is the effect of the signal. So there is a long learning path ahead of us to try to understand this. This is very early days. At the same time, the enteric nervous system is beginning to get explored. We have a fellow here who just started, actually, who is now implanting electrodes in the gut, trying to communicate with neurons there and see how those signals convey up to the brain. Very early days, and even the configurations of electrodes that we use are the same as the ones that were used in the early explorations of the brain. So it is the Wild West. We're learning at an exponential pace, but it's super, super exciting. I think the gut will become the next frontier, especially its connection with the brain, for people who do bioelectronics and neuroscience.
Well, thank you. Yeah, I can imagine it being definitely a field that we can further explore with issues with, for instance, things like motility that we struggle a lot sometimes with these patients that have these conditions. So I could see. Well, it's exciting.
I wanted to ask Prof. So interestingly, I just probably go back to the first few slides about Parkinson's disease. I was on call a couple of weeks ago. We had a patient with a bleed, but also we picked up they actually had signs of Parkinson's. So the device and the kind of brain-machine interface, are you saying that we should purely focus on the device, or would the device, in addition with medical therapy for Parkinson's, be the way forward? Or do we try medical therapy first? If medical therapy fails, do we then move on to the device? It's fascinating. Like, what are you thinking in terms of the routes? Because clearly you showed in the video that in terms of bioelectronics, massively improved the symptoms that are affecting patients with Parkinson's. So to me, it seems the medication, probably we could skip a step, go straight towards that. What do you think?
Well, this is not the current practice today, but it could very well become the current practice that you skip medication. One of the questions that still remains to be addressed is how does habituation work? There is some work in epilepsy that shows that if you stimulate electrically at the focus of the seizure, then after a while, the brain figures it out, and the frequency of seizures begins to increase again. So this is obviously bad, right? Such habituation is not a good thing. But obviously, this is something that also can happen with medication. So exactly what treatment should be prescribed when, it's still an open question. I was reading the recommendations of the James Lind Alliance yesterday for Parkinson's, and I think that's the first question. Exactly what type of treatment should you envision prescribing, right? It's a very important question, but I think it's still open. There are synergistic effects when you do both chemical and electrical stimulation. For example, people who look into spinal cord regeneration after injury, they have seen both in vitro and in vivo that there is synergy between neurotrophins and electrical stimulation.
Right.
The same holds in tissue engineering context. And we're now exploring this in the case of brain tumors. Can we combine electrical stimulation at the right frequency with chemotherapy to achieve a better outcome?
Fantastic. I do have some more questions if you have time.
Please, yeah, I have lots of time.
So we've heard over the past couple of days about devices, and everyone's doing brilliant work in devices. I'm not an expert in that, but obviously very interested in the interface. Say if I had a device which was an app, the kind of barriers that I face are much less, I guess, compared to, say, a bioelectronic device, which is brain related. And I noted that in your presentation, you said, okay, probably in a couple of years, we can get this done. Are there similar barriers to all devices, or would you say, depending on the organ, there's tighter control? What's your experience?
Yeah, I mean, the drug delivery device that I presented is a class 3 drug device combination. The regulatory pathway is as extreme as it gets and very expensive. But I mean, that's what you have to do. It just costs money and time to make sure the device is safe and effective. And it's a well-known process of what you have to do to get it to the clinic. It just takes a lot of money and a lot of time. That's what it is. The ethical questions are fascinating, and they're very different when you act on the brain than when you act on the heart, for example. Because the brain is the seat of consciousness, right, is who we are. And this raises questions of agency, for example. Can you claim that it's the device that made me do it? There are examples of patients who were explanted. They had a stimulator for epilepsy, and that was removed because the company that supplied this went bankrupt. And they felt like they lost a part of themselves. So the device becomes part of yourself if it's in the brain. There are examples in cochlear implants of the ethical questions raised there. It's a fascinating topic.
Absolutely. Do you have another question, actually, is around the aspect of seizures? With kind of my background in internal medicine, there's a lot of cases that I come across where we do have patients that when we're on call, they start having seizure-like activity, and we get quite confused. So we'll scan them, refer them to neurologists, and often that difficulty between determining, is this a true seizure or is it a pseudo seizure? Have you noted from your work through, all the devices that you're using, that in a way, maybe there's a better way to distinguish between a seizure and pseudo seizure with new devices as opposed to how we're doing it at the moment?
I mean, continuous monitoring would help address this issue, but that's done usually with cutaneous devices. It's easier to implement. Those systems are coming online. We can envision electrodes that record with very high signal to noise ratio over a period of several months. Today we can do that. Typical electrodes, this silver chloride cutaneous electrodes for EEG, ECG, they would dry in the field after about a day or so. But through some innovative materials research, we now have electrodes that can hold a good contact, both electrically and mechanically speaking, for months. So rather soon, you will start seeing continuous monitoring systems that are very capable, that can hold the signal for several months. And those will help elucidate these questions. Another topic of research that's emerging is, so in neuroscience, there are two schools of thought today. One says, let's stick 10,000, a million, a billion electrodes in the brain to try to understand connectivity. And there is, so this is like a race to the moon, who will do the probe with the most electrodes. But then there is another school of thought that says, let's focus on one part of the brain and try to understand much more about it. So look not only at neuronal signals, but look at the cerebrovascular unit, and look at what happens to metabolic activity, what happens to electrolytes during, before, and after a seizure. So this requires a very different type of device that will measure simultaneously and in the same location in the brain, not only electrophysiology, but also metabolic activity, ion concentrations, oxygen, ROS, what have you. Those will lead to a much better understanding of how the spiral between low metabolism and aberrant electrophysiological activity works.
Absolutely. We do have time for one more question. Lady Catherine, do you want to lead that? I think it came in the chat box.
Yes. So Maheen is wondering how much expertise is needed for the proper application of such devices in the clinic. Does the training aspect for healthcare providers ever pose a barrier?
Yes, it does. For example, for the data I showed here on cadavers, this is done at the Evelyn Center in Cambridge, which is a surgical training center. And we are training the neurosurgeons who are going to be placing these devices on technique. We have to develop the surgical techniques as well. So the lab is very interdisciplinary. It's co-led by Damiano, who is a physician, he's a neurosurgeon. And the expertise ranges from physics of ion transport all the way to surgical techniques. And you need that in order to be able to do the effective translation of new technology to the clinic.
Perfect. We have Faisal also from Dubai. I don't know if he can hear us, if he's on the line. Oh, there he is.
Hi, everyone. Yep,
Hi.
nice to join in, and excellent presentation from your end, Professor George.
Thank you. Thank you.
My question really is along the lines of how much has the current situation with the pandemic really either affected or enhanced your progress through this research? Do you see that as something that's accelerated in the direction that you'd wanted it to, or how different has that panned out?
No, for us, it was, we had to shut down our lab. There were clinical trials that stopped. So for us, it wasn't an accelerating factor, but rather a very strong break to quite a lot of our efforts. And we still haven't recovered from this. We're still not open in the same breadth as before. There are limitations. We cannot go in at weekends. So we're still affected, but yeah, there was collaborators within our center moved on to develop COVID-related diagnostics, ventilators. So people kept busy and tried to contribute. But by and large, our own work slowed down.
Right, and besides that, I think you've still managed to, as a team, come through so many of these achievements and collaborations. So really appreciate the work that you're doing. Thank you for that.
Thank you. Thank you.
Well, thank you very much, Professor George. Truly a fantastic talk, and it's generated a lot of debate and discussion. And I agree. I think this is an area that we definitely need to focus on. It's going to be impacting healthcare in a massive way. So thank you for spending the time.
Right, a pleasure. Thank you very much for having me.
Great.
Bye.
Okay, everyone. So that's the first talk done. We're going to come back at 1400 UK GMT. And as I always say, take a break, have something to eat or drink, mobilize, very important as we sit down for the day. And we'll be back shortly. All the best.
All right, well, welcome everyone to the Clinician Engineer Hub virtual conference. My name is Faisal Nawaz. I am your host for today, co-hosting with Dr. Neil Sharma from the UK and Dr. Lady Catherine from the US. And we have an amazing lineup of speakers ahead of us with our second talk starting with Professor Anthony Bull. Professor Anthony is the Professor of Musculoskeletal Mechanics, Head of Department of Bioengineering at Imperial College London. He is pioneering in the field of sport biomechanics, injury biomechanics, as well as biomechanics of aging, including osteoarthritis. His work has led to various research publications and accolades in the field of musculoskeletal engineering, including his role as the director of Musculoskeletal Medical Engineering Center. Professor Anthony, the stage is yours, and we are pleased to have you with us today.
Thank you very much, and I really appreciate the welcome, and I'm now going to share, and if you can confirm that you can see that at this point.
Yep, perfect.
Wonderful. I will just pull up my laser pointer. Okay, wonderful. Well, it's a great pleasure to speak to you, and I look forward to the interactions afterwards in the discussion. So I put up a slightly provocative title, and I think frequently when we think about engineering and medicine interfacing and working together, we think about a joke like this, where people will come together and they end up speaking a different language. There are generally puns associated with this, and they go away with somebody looking like the fool. And what I'd like to do is to propose a different way of working with a few examples that I have. So my examples are going to be in the area of trauma. So you'll see some nasty images coming up right now of traumatic incidents. And I'm going to talk about traumatic amputation and heterotopic ossification. And the first thing to say is this red circle that I have there is making sure that we place the patient at the heart of everything that we do. And so as an engineer, and my original background is mechanical engineering, I'm confronted with this and I'm thinking, well, what should I do about this? What is the importance here, and how can an engineer contribute? And of course, the story is that we hear that people have these wonderful reconstructions, they have an amputation, and they end up competing in the Paralympics perhaps. But of course, actually, for many people, that's not the way it goes. The way it goes is they might end up in a wheelchair, unable to walk on their sockets. They might end up with the aberrant formation of bone in their stumps called heterotopic ossification, shown here in this CT scan image, and pressure sores resulting from the pressure between the socket, the bone, and the ectopic bone pushing through. And this image from Karl Potter's work shows the surgical excision of that. It looks like an alien coming out, and it really is an alien form of bone, although it is forming like bone. And of course, there are many different ways that we can then implement prostheses. But if you look here in this image, you see someone who is an amputee on one side and has a prosthesis. And on the other side, you can see that they also have a joint replacement. And this is one of the key problems that happens with amputees, is they wear out the other side. And so what is it that makes one person an elite athlete and the other one in a wheelchair? Are there differences in injury mechanism or the initial and definitive treatment? Are there differences in the prostheses and the rehabilitation that they received? And if we were to answer these questions, and this is now the engineer with the green hammer there. No, this is the surgeon, I mean, with the hammer. Of course, the orthopedic surgeon is often compared to that. The clinical approach may be to conduct control studies where we will look at different ways of rehabilitating, different ways of doing the surgical, definitive surgical reconstruction. Or we will obtain lots of empirical data and come up with answers. But of course, these are not mechanistic. And what they do is they require us to have many patient subjects who are the guinea pigs in this. And we'd like to bypass that guinea pig stage. I will say that there is some very good work ongoing in this domain, and I'm co-lead for the advanced study, which is a 20-year follow-up of the major war wounded of the British military from the Afghanistan warfare. And we are doing control studies, and we are doing empirical analysis of that. The work that I'm presenting in this area is part of a center that I lead called the Center for Blast Injury Studies at Imperial College, which is associated with a veterans charity and with the British military. So those would be some of the clinical things that we might be interested in, but there might also be scientific questions that we're interested in answering. And us engineers in universities also use the scientific method to answer questions of science. What is the ectopic bone? How and why does it form? Or even more in a musculoskeletal whole body sense, what is the performance limit of someone with an amputation, and what are the determinants of that limit? And why do people get arthritis in an accelerated way? 65% of amputees have arthritis in their sound, healthy, intact limb. So what I'm going to do is I'm going to use my hammer. And so this is now a wonderful image copied after Blake of Newton, where Newton is measuring. And of course, the great scientists, the great engineers, we measure quite a lot. And so I'm going to talk a little bit about measurement as part of what I do. Of course, biomechanics is engineering mechanics applied to living systems, where we're talking about forces, deformation, flow, and movement. And actually, we can apply them to the problems we've just posed. The mechanics of materials, this ectopic bone, the treatment, the mechanobiology, and the biomechanics in rehab, and then mechanical design for prostheses. So I'll give you a few examples of some of these as we go through, and I'd like to broaden the discussion as I come to the end. And as I broaden the discussion, I'm going to talk a little bit about how we might develop and enhance an ecosystem for this kind of interdisciplinary work with engineers and medics. So I'll start with talking a little bit about the mechanobiology of ectopic bone formation. And really what we're talking about is, how does soft tissue become bone? And well, tissue can become stiffer depending on loading and the loading of the neighboring elements if we use a computational method. And we know that inflammation causes some cells more likely to become bone. And that inflammation occurs obviously close to the site of damage, of trauma. And so if we can influence the substrate stiffness, we can change the chance of these cells differentiating into bone. And so we established a very simple probability-based function, which really is telling us how a material is likely to change its behavior into bone, and then how we can model that change in bone. And of course, we test that first in the usual testing ways, which is where we test it to see if we can mimic the normal shape of bone and the normal trabecular structures of bone, as we have here, and this is done using that model. But of course, what we need to do is see how we can apply that to soft tissue forming bone in amputees. And just a little bit of subtlety here. The typical bone density changes that people model is using this function. Harry Weinant and others put this forward computationally, where if your strain energy density, or whatever the function is that you choose to use, is within a zone where the loading on the bone is within some kind of normal zone, then the bone won't change its density, won't change its properties. That would be called the lazy zone. But if you load it to some higher extent, you will get bone formation. Or to some lower extent, you will get bone resorption. And the bone will either resorb fully, or it'll change its density and become weaker and less stiff. And this is typically how it is used in computational biomechanics. But of course, one of the problems there is it presumes that you can go to a very high level of signal and you will still have formation. Yet there must be some saturation, both in resorption and in deposition. Of course, in resorption, it's obvious. We know, for example, people who are paraplegics, they still have an intact bone shape, even if they're not loading their bone. So it doesn't resorb away to zero. And so we need to come up with a way of putting that into our models. And so that's something that we've been working on and coming up with the limits on that. And so we end up with this kind of schematic where we have a mechanical stimulus, strain energy density, something like that. We have our mechanobiology of blast trauma that I showed you in the first equation, and that tells us how tissue can change, and then we will change the tissue density, and it might become bone, it might become less stiff, and we change the tissue stiffness, and that then influences the mechanical stimulus in our computational finite element model. And so using this very simple approach, we can now start modeling how ectopic bone forms, and also how it can change its shape and how you might mechanically intervene in that. So for example, these are some of the shapes of bone, and I hope that you can see some of these animations as we go through, where by changing, for example, the position of the prosthesis, we can change the loading in an abduction or adduction sense. And these are representations of X-rays that we would receive. And you can induce extreme volumes of ectopic bone. You can induce very low levels of ectopic bone. Or if you increase your medical intervention through tourniquet pressure, for example, you can get a very different shape of ectopic bone that forms. And these represent real clinical conditions. And so what we're saying is that actually through a mechanical change, through a mechanical intervention, you can minimize, even close to zero, the amount of ectopic bone that is formed. And so this biomechanical understanding will allow us to intervene. And we really are able to simulate the types of X-rays, the types of ectopic bone that you see, this sort of beetle nest form, this kind of spur form that we see, these kinds of spurs. So that now opens the door to a mechanical intervention for ectopic bone formation. And of course, as engineers, we sometimes need to get involved in far more difficult stuff. That was a nice computer model that we can validate in different ways. But the only true way that you can validate this is by actually taking a person or a biological model, by inducing the ectopic bone formation, and by following its progress, and by changing the mechanical loading environment. And so this is a model that we have been establishing. The video is not working just at the moment, but that's fine, that we've been establishing in our animal model. Okay, I'll just move on and say that now what we're doing is we've obviously moved this into 3 dimensions, and we're exploring how changing the muscle loading as well as the external loading can change the formation of ectopic bone. Why is that important? Well, if you look at the image on the left-hand side here, you will see that if you do the amputation at different levels, you change the muscles, the adductor muscles that are on the medial side here. And by changing those muscle insertions, you can actually change the loading in the bone and change the loading in the soft tissues. And so there is the idealized idea that if we were to change the way we reattach the muscles, we can also change the formation of ectopic bone and therefore allow these individuals to walk on their sockets. So I'll move off mechanobiology and I'll just go into more whole body biomechanics and talk about a little bit about knee loads in amputee gait. So this is a very simple inverse dynamics understanding of how the human body works, where you understand the position and external loading on the human body. You understand the mass and size of the body segments in a dynamics sense, and you understand how the muscles create force through their moment arms, their lever arms around the joint center of rotation. And through calculating using an inverse dynamics approach and understanding the anatomical positions of all the ligaments, the bones, and the muscles and their cross-sectional areas, you can calculate the joint reaction forces and the muscle forces that produce the motion that you're measuring. And that allows you to then look at tissue stresses. I need to undo this, which will undo the laser pointer. There you go. And so these are some very old videos from my lab where we will measure someone in the lab. We obviously will then digitize that using standard motion tracking technology. And then you can see here an animation of the musculoskeletal model that we have underlying that, where we represent each muscle as a line of action, as a moment arm, and as a cross-sectional area, so as a maximum muscle stress that it can potentially give. And then we can apply that to quantify how those muscles are inducing the motion that we have measured. And here we're just visualizing the activation of the muscles as they go deeper red and thicker. And you will see that gait is an extremely optimized activity because the muscles don't work very much for much of gait. Actually, it's just swinging like a pendulum. And of course, that's well known. It's highly optimized. Of course, you now have to apply this to an amputee and specifically to understand how the tissue stresses are influenced by the amputation, by the anatomical deficit. I just want to say that these models have to be validated. And of course, the way they're validated is quite difficult. There are not many people who would allow you to instrument their muscles to quantify the muscle forces as they move, for example. And so the way that this is done is by implanting a joint replacement. So these are individuals who might already have joint replacement surgery. By implanting that and having sensors within the joint replacement that directly measure the medial and lateral joint contact forces, for example, in the knee or the hip joint contact force. This is part of a national study, an international initiative called the Knee Grand Challenge, and the citation will come up just in a minute. And so they, for a number of years, had a challenge where people were given input data, but not the actual measured results of the medial and lateral joint reaction forces, and then you had to simulate that and predict it, and then the competition to see who won. So this was from the 6th Grand Challenge data, and this is showing to you the experimental data that we received afterwards in the blue, and the white is our calculated contact forces using these musculoskeletal models for 2 different types of gait that this subject underwent. And so that shows that we have confidence in the joint reaction forces and therefore the muscle forces that produce those for this type of model. And we can now use it for amputees. And so what we have been doing is we've been doing many studies with our amputees, above knee, below knee, etc. But there are some fundamental questions that we're trying to answer relating to the questions that I posed right at the start. We know that knee osteoarthritis is related to movement biomechanics and the mechanical loading of the joint. So this type of technology is very appropriate to use for this. And so what we did is we developed a transtibial amputee model. We conducted the experiments. And this is just my single highlight summary slide. And it's stark and very important. The first point to note is that the intact knee on the contralateral side, so these are unilateral transtibial amputees, has a significantly higher joint reaction force on the medial side, which is the point at which you get knee osteoarthritis. What's very interesting is that the medial joint reaction force on the amputated limb and on the control subjects were almost exactly the same. And so these individuals, who, by the way, have gait that is indistinguishable from healthy normal gait. If you were to see them in the street, you wouldn't notice it. If you were to measure them in the lab, the kinematic parameters and the flexion, etc., are basically the same as for a healthy control group. But the internal forces that produce that are so significantly different for the contralateral healthy limb that they will get accelerated osteoarthritis and wear their other limb out. We've also looked at above knees, for example, and we've been looking at comparing the muscle volumes as well as producing the musculoskeletal models like I showed previously. But I'll just show you something very simple and very stark here. So here we have our first 6 data sets or 7 data sets of these amputee muscle volumes, these first data sets. And then this final bar for each one of these is a healthy controls. And what you will see is obviously this very significant difference between the muscles of the glutes that are working far harder in the amputees, of course, compared to the controls, and the muscles of the quadriceps that are not working nearly as hard as compared to the controls. That's obvious. You will see why that is, of course, because the quadriceps cross both the knee and the hip, and so they're unlikely to be able to work so far. However, what's powerfully important for these individuals, if, for example, we look at the image on the right-hand side, the hip joint contact force for the healthies is not quite, but close to half the force and the hip joint contact force of the above-knee amputees. And therefore, there is really the potential for this very severe overloading and wearing out of the joint. The total muscle forces across the hip are far higher than for the healthy controls, which means fatigue is a very significant problem. And yet these individuals have learned to walk in a way where the ground reaction force, the force between the ground and the foot, is almost indistinguishably different between the healthy controls. So we need to start thinking about how we can intervene. And this is a very simple example. So this is a summary again of the hip contact force between the amputees and the healthy controls. The rectus femoris force, which is a very small muscle which fatigues in the amputees and in the controls. And if you were to change the initial surgical intervention and therefore change the muscle moment arms, you can lower the hip joint contact force and you can lower the fatigue in the rectus femoris. And so this kind of mechanical analysis allows us to change surgical interventions at the point of definitive amputation. My final technical examples are not very technical, but they're about design for amputees. And if you look at this single amputee, this is an above-knee amputee. The socket, the stump is well shaped for a beautiful socket because that's a nice shape. And yet we have learned that above-knee amputees don't function nearly so well as through-knee amputees, where you have the distal end of the femur, and so you can have load transfer. And so now there is a change in surgery if you have enough of the limb remaining that you try and keep the distal femur, whereas previously those who make the prostheses and the sockets will have preferred this type. But of course, there are other ways of intervening, and one way of intervening is, instead of wearing a socket, it's to have osseointegration, where the implant goes through the skin into the bone directly, and you can have a mechanical connection between the prosthesis and the bone directly without having to go through a socket. Of course, there is the potential for infection because you have an open gap forever. And so I don't really want to go any further on that, just to say that there's a lot of active ongoing research about the long-term effects of this and how to optimize this. But something that we in the group have been doing and working on quite significantly, and here you see a stump with ectopic bone, so this person cannot walk on that socket, on a socket. We really want to convert that to a through-knee amputation and provide a distal load-bearing end. And very simply, you put a plug on the end of the bone. We've published this. We're working on now translating this into human trials. And this is a way of creating that mechanical design and that mechanical load to protect the bone, so you have load transfer through the bone, but also to reduce the pain that people have when walking on that socket, without having to go through the skin and therefore induce potential infection. Another example is that if we're able to achieve through-knee amputation, if you look where the center of the knee is, the center of the knee then, if you have a prosthesis, you require an above-knee amputation to create space for that prosthesis. If you have a through-knee amputation, then your knee mechanism is below the knee center of rotation. And so you end up with extremely clever mechanisms that have a moving center of rotation. But in fact, in most countries, there is a lack of resource for these types of prostheses, and they tend to, for example, be given the International Committee of the Red Cross prosthesis, which doesn't have a simple through-knee mechanism. This is an early design. I can't put up our current design because we haven't yet managed to copyright the design or patent it. But we're currently translating that for our work in Cambodia and Tanzania and Rwanda. And it's functional and it's maintainable locally. And so as part of that, I just want to, if you don't mind me advertising, we're running a global conference this coming weekend, Saturday and Sunday. And you're very free to click on that link. Just look up University of Global Health Equity and Imperial College, and we have our conference starting this weekend. So I just want to thank the people who are working on this and our funders. And in my last few minutes, what I would like to do is I would like to do a little bit of a broader discussion to go back to my title about the engineer, the scientist, the clinician, the patient walking into a bar. And I have these individuals coming together, and this is a shell of a building. This was a photo from a couple of years ago. And I just want to talk about creating a translational biomedical engineering ecosystem. And why do I think this is important? I think this requires a new thinking in academia in particular. So we know that universities are really good at disciplinary-based research. You know, we have my department of bioengineering, for example. In chemical engineering, you have industrial biotechnology, materials, biomaterials. You might have biomechanics and mechanical engineering or surgical technology. So you have this disciplinary depth. You might even have a really good interdisciplinary and collaborative culture in your university. You have education and people and research. But actually, there are some things missing to have real translational benefit. And I think the things that are missing are some of the things I've put here: a co-location space, real clinical leadership and academic leadership from the engineering side, where they speak the same language and they can work together. You need critical mass in key areas, and frequently critical mass is not present. In many universities, you have 1 or 2 engineers working in, let's say, orthopedics, my area. And that's not sufficient, actually. You might have 1 leading clinician who you can engage with. But you need active, supported co-location facilities, maybe even having the patients in. So this is now the image as it stands of our building. We finally opened, we've been moving in during lockdown, and we have these researchers where we've co-located researchers, clinical and engineering, who are all working in interrelated domains, going from the brain at the top, neuroscience, neural engineering, all the way through to the heart and musculoskeletal technologies, including regen med. And on the first floor, we haven't yet done this, but we're building a clinical interventional facility where we can do operations. And so we will truly be bench to bedside. And so when I go in the lab now, I'm in the lab with all my clinical colleagues and all my engineering. Another key pillar, I think, of this translational ecosystem is to have some kind of an accelerator structure. So we were very pleased to receive funding for this through the Wellcome Trust, and Anne Rock, who is a project manager from industry, from the orthopedic industry, where we have embedded translational project management within the university. And in fact, that's taken away from the academics. So I, as an academic, I will put my technology, my intellectual property into this system. And of course, they'll come back to me because I may be the expert in the technology, but they will manage the resource, the money, and they will manage the translational process, which might include putting this under a quality management system, which we have within a university, which is extremely rare. We have an innovation panel with people from outside and entrepreneurs and residents who give very sharp advice and in fact will cull projects very early on. So there's a structure to this that I think is key and we need to do for this type of translational research. And I think you also need people who can be T-shaped. You need graduates who are T-shaped, who are able to have the depth in their discipline, but are able to speak across. And these are just the educational programs that I think are interdisciplinary enough. We have biomedical engineering and molecular bioengineering undergraduates. The ones in the middle are our MSc programs, our taught master's programs, and the ones in the bottom set are our master's by research programs. But we recognize there were still some gaps there. And so in the last couple of years, we've introduced a few others. So our medical students now at the university can spend an additional year before their final 2 clinical years to do an intercalated Bachelor of Science in Biomedical Engineering, where they are embedded in research teams with our engineers and scientists. Likewise, we've done the same at the master's level in engineering for biomedicine master's program. And we will be launching the year after next an undergraduate degree in biomedical ventures, which is really at this nexus of industry, translation, entrepreneurship, engineering, and medicine. And so we're excited about that. And this is really my final slide. And this is just one of the research groups that I belong to in the Center for Blast Injury Studies. And the colored circles represent the different expertise from these individuals. So the orange colored circles represent clinicians. The red ones represent engineers. The green ones, physical scientists. The yellow ones, life scientists. And then there are 2 purple ones with a designer and a historian who are embedded as part of this center. And I think that's what you need sometimes to have significant clinical benefit. And so there is no punchline to this joke. They didn't walk into a bar. they walked into a translational biomedical engineering ecosystem, which is really established for clinical benefit. So thank you very much for your time, and I look forward to the discussion and the questions.
Thank you, Professor Ball. That was truly remarkable. I'm going to ask Faisal from Dubai and Lady Catherine from the Cleveland Clinic to lead the questions and discussion.
Well, thank you very much, Professor Ball, because this is certainly a topic that I feel that could have a lot of impact. Particularly, I come from a region that has been in civil war for a very long time. And one of the means of violence is actually putting mines in the soil, and as people are walking by, they just explode and it causes damages to their limbs. And I feel that I come from Colombia originally, and sometimes there are not enough resources, and I think that people certainly struggle a lot with this issue. So thank you for doing your work on this area. I do have an initial question for you, and it would be, let's say I have a patient who, for whatever reason, had either above the knee, below the knee amputation. How can I guarantee, or how do you see the process of going from the amputation to doing all the analysis to creating the proper prosthesis for this person? Because I could imagine that it should be an individualized process based on what you've told us. So how can we facilitate that process?
Yeah, I think that's a really good question. And I think, first of all, to your comment about landmines, for example, and post-conflict injuries as a result of those. I think the first thing to say is that there is really good news. I think the world is getting rid of landmines. There are many countries that are now landmine free in the last few years. And so the international effort on that has been pretty successful. However, they still remain. And there is a very specific case where children are more likely to be impacted by landmines. They're more likely to pick up these things when they see them, and they're more likely to be injured very severely, not only in their lower limbs, but also their upper limbs and face, because of their close proximity to the ground. And so I think the first thing to say is that we have identified that there is there's a gap in knowledge in how to treat pediatric blast injuries specifically. And so we established 2 years ago something called the Pediatric Blast Injury Partnership as an international partnership. We identified the first gap, which was that the knowledge about specific treatment for children was missing, or at least it wasn't promulgated. And so we collated that and pulled that together with very broad collaborative help across the world. We produced a field manual, which is now in use across the world. It's been translated into Arabic and French, and it's now being just used everywhere as a way of capturing the knowledge we have about how to treat children. Children are not just small adults, they're small human beings, and they need to be treated differently for these types of injuries. That's the first thing. The second thing, in terms of subject-specific or patient-specific treatment first, and then prostheses and rehabilitation. The first thing is you want to try and salvage the limb. And so we have other work on limb salvage, which I didn't present here, which is work that we're leading together with the American University of Beirut. They are a regional center for us for a region where very severe extremity injuries are present consistently. They were obviously very severely influenced by the largest civilian explosions seen, other than nuclear explosions recently, where they had very many extremity injuries as well. They are a link into Gaza for us, and obviously Yemen and Syria, where there are hundreds of thousands of amputees. So the first thing you want to do is actually save the limb. And that requires novel reconstructive technologies. And many of them are very subject specific. So if you have a defect, for example, in a bone or a muscle, you need to close that defect, you need to fill it with something, and you need to make sure that it regenerates. And one of the difficulties there is that you need to do that in a way that requires maybe effective medical intervention at the first stage, but you don't want there to be multiple interventions required. You want to minimize the number of procedures. And so many people, including us, are working on one-step procedures rather than having a definitive procedure that might be 5 or 6 operations later. So that's one way that we're trying to address. Another way is to try and use modern technology to minimize the need for technologies, for example, CT scanning, medical imaging using computer tomography, X-rays, where you can create a 3D reconstruction of the 3-dimensional shape to then create your subject-specific technology, reconstruction, amputation. And some underlying data-heavy technologies, statistical shape modeling is one of them, have been devised where you can effectively use a planar X-ray to recreate what the 3-dimensional intact shape would have been, to then create your custom biomaterial shape that you can then use for as the gap filler to replace the defect. So we're working on that as well. And I think finally on the prosthesis, customizing the prosthesis, well, there are many different ways it's customized. The alignment has to be customized, the stiffness has to be customized, the foot has to be customized, but also the socket has to be customized. And that is really an art. It's very difficult. It's done manually typically. It requires huge training and huge resource, and the world is under-resourced in P&O, prosthetics and orthotics professionals. And so what we as engineers and clinician engineers have to do is we have to find technology that is appropriate, but reduces the requirement for this great level of expertise. There are many people around the world doing that. We're doing our own little piece on that, but it's not a solved problem yet.
And definitely, again, the impact that it could have, it would be tremendous. So we're excited to see what's to come.
Thank you.
Lady Catherine, Faisal?
Yeah, very well phrased in terms of your answer there, Professor Anthony, and even the presentation as a whole. I think it touched on the important factors of where we overlap in both clinician and engineering roles. And I think I'm very impressed seeing how much background knowledge goes in, even from an engineering point of view, into the healthcare industry. So we have lots of questions here coming in from our social media as well as Zoom platform users. And one of those have been very exciting in terms of implants. So implants for amputee has making sure that we're looking at an era for precision-based care. How has this influenced your choice of implant in the sports industry in this aspect?
Oh my goodness. Okay, so so my work in sports has been very much related to either the overall musculoskeletal function, so optimizing muscle contraction to achieve activities. And my main work in that has been to do with rowing, working with the British Olympic rowing team, or in cricket, working with the MCC, the Malliaras Cricket Club, the custodians of the laws of the game of cricket. And I've enjoyed that work. But if we look at how that relates to injury and then maybe implants, one of the key areas that is significant in this is joint injuries, and so ligament injuries, where ligaments rupture. And when ligaments rupture, then you end up with an instability in the joint, where you still have the muscular contraction that can drive the motion, but you don't have the tethering of the ligaments to give you a stable base for rotation of the joint. And some ligament injuries can be accommodated by muscle co-contraction, where the mechanical environment has changed, and then you need to implement new ways of contracting your muscles. And so one of the technologies that we've been working on, and one of my postdocs is taking as a spin out right now, actually, I have some documents to sign today on that, to hand over the intellectual property to the company, is a functional electrical stimulation technology where you can stimulate the muscles externally. And if you have a smart way that you can monitor the motion of the person, you can then, in a smart way, drive the stimulation of the muscle without having to tell their brain to do it, but you just tell their muscle on a surface with a surface stimulation. And there is evidence from the literature that once you then learn new ways of contracting your muscles, your brain then learns that and you don't need the external stimulation anymore. So that's not a prosthesis response, but it is an important response to deal with ligament injuries or instability of joints in other ways. But of course, in the end, if you have a very severe injury, you need to have some kind of prosthesis or surgical intervention. And in this way, the world has gone round and round with many different approaches where you use autologous material, tendons, you used grafts from cadavers, or you use prosthetic material, either resorbable or permanent. But all of these require mechanical fixation that is strong and stiff, very optimal positioning so that you don't then overload the joint. And for those of us who come from a traditional mechanical engineering background know that if you have only a slight overload, you can induce fatigue failure over a long period of time. And so actually, although many people are successful in returning to sport with these types of procedures, many of them will go on to develop accelerated arthritis due to the mechanical overload. And so we haven't got to the stage yet where we are able to quantify clearly the localized mechanical environment of the tissues and of the cells that then produce the response that is detrimental, such as osteoarthritis and others. So I'd say there's a lot of work that still needs to be done on that.
Right, absolutely. And keeping in mind, I mean, the aspect of how much of that functionality can be restored, there's a lot of these factors that interplay, as you mentioned, with the fatigue and potential implants that then accordingly fit into these roles. And the aspect of functionality, and you mentioned about how you follow progress for example, ectopic bone formation. I'm curious to know, and perhaps you could elaborate further on how this progress is followed through your modeling techniques, if you incorporate any form of predictive modeling or artificial intelligence in terms of really seeing how the progress of such aspects goes forward.
Yeah, so the modeling is predictive, right? It's basically saying this is the loading environment, and then this is how the bone forms. We're not using any artificial intelligence in that. We are using that for our control of the functional electrical stimulation, for example, but we haven't done it for this. One of the reasons there is that we have very few data sets that we can actually validate these models with. It's almost impossible to do so. You would have to X-ray someone serially over a period of time. And of course, we want to minimize the radiation dose, which is why we need to develop animal models of this. There are some animal models of this that are available worldwide. We believe that there are some issues with those because you need to create something that is as close to the human as possible. And so you need to create both the blast wave that produces the injury, you need to produce the fractures, and you need to produce the amputation simultaneously. And so no one has done that, which is why we've had to work on that to induce that. So where the work is going, the work is producing that model that will allow us to follow the progress and therefore validate and verify these models that we believe are pretty robust. And then secondly, those models will allow us to introduce mechanical interventions. And we can conceive of mechanical interventions, of course, by putting, for example, a socket that you then mechanically load the stump to change the formation of this bone. And just one other point on ectopic bone, sometimes, very infrequently, ectopic bone is desirable. So normally it's messy and it forms this kind of spider's web, or it forms a spike that produces pressure sores. Sometimes ectopic bone forms a nice cap. And that nice cap is like the implant that I showed you for an above knee amputee. And so wouldn't it be amazing if we could drive the mechanical loading to produce ectopic bone as a cap without having to then intervene surgically? So that's a holy grail. I don't know if we're going to get there, but it's a nice thing to think about.
An open thought for sure. And we're really happy that you've shared these insights with us. And I can tell you for sure that the next time we see an engineer and a clinician walking into a bar, it's going to be a very promising picture ahead. So thank you, Professor Anthony, and over to Dr. Neil.
Want to second what Faisal has said. Absolutely brilliant what you're doing. The impact that you're creating is phenomenal. So that's why we wanted you here as part of our conference, because we know that you're doing fantastic work. Really appreciate the time that you've put into this presentation. And we're going to close this session now. So we're going to be back at 1500 UK GMT. So like I always say, take a break, have something to eat and drink, stretch your legs, and we'll be back shortly. Thanks once again, everybody. Thank you.
Bye now.
Sure. All right, so welcome everyone to the Clinician Engineer Hub virtual conference. My name is Faisal Nawaz, and I have my co-hosts here today, Dr. Neil and Dr. Lady Catherine, coming in from the UK and the US respectively. Today we have a special guest with us, Dr. Shez Parthovi, who is a worldwide lead in healthcare, life sciences, genomics, medical devices, agriculture, and many other fields of digital transformation as part of the Amazon Web Services. He has led pioneering roles in enhancing patient satisfaction and analyzing software tools that can help organizations develop better ways of digital transformation. Dr. Shez Parthovi, the stage is yours. Happy to have you share your screen.
Terrific. I will do that. Let me bring up the screen and go into full screen mode. And Faisal, can you see my screen?
Perfectly.
Terrific. All right. Well, good morning, good afternoon, good evening, depending on where in the world you are. It's a real pleasure. Thank you, Neil, for the invitation, and Faisal, thank you for the introduction. What I thought I'd do is going to spend maybe 20 minutes and tell you a little bit about how AWS helps accelerate various things. In particular, we'll lean in on research, and we'll leave time for any discussion or questions that might come up. Now, in case you are not familiar, AWS has been around for about 14 years, but what most people may not know is about half that time we've had a dedicated healthcare life science practice. And that really means that we've had the pleasure of inviting folks that have been at the bedside, they've been at the bench, whether they're researchers, physicians, nurses, digital officers, biochemists, and genetic experts to come and join the practice. And so when what that means is that when you work with the AWS life science practice or healthcare life science practice, you won't have to explain your business. Most of the folks have been part of the industry for a long time. And it's really a pleasure to be able to work with, oops, I think I clicked a little too many clicks here, to be able to really work with a large number of organizations across the world that work on AWS, whether they're giants like Pfizer, Merck, BMS, Moderna, whether it's young companies, whether it's partners, and across the world like the NHS and NHS Digital, various trusts, whether companies like EMIS in the UK or Black Bear. One of the things that we're delighted by the fact that it's not just that we have this large and growing network of customers, but that we never actually forget that if you look at the mission and vision statement of almost any one of the customers that we work with, any of the organizations and partners, you'll find a common word in all of them, and we never forget that. It's invariable. You'll find a word, a reference to a person, a patient, an individual, a member, because in healthcare life sciences, it's almost every organization is really working hard to elevate the human condition. And our healthcare life science practice in AWS really is quite aware of that lofty mission. And we're delighted to be part of the organization, working with organizations that help do that. So when we talk to organizations about how can we help accelerate clinical research, any kind of research, the discussion often leads itself to something else that is a precursor. So I want to start there. The discussion often leads to this idea of data liquidity, because at the end of the day, to accelerate research, typically it begins, you want to do faster drug discovery, you want to do faster anything, your synthetic arms in your clinical trials or what have you. But when you really dive into it, you end up with this discussion, well, our data's in silos, this is tied up, we really can't liquidate that data, we don't have interoperability, we can't bring it all in. And so let's just start there, because what I'd love to tell you is how we help achieve data liquidity, and then we'll tilt into talking about some really specific examples of how that helps accelerate clinical research. So when you talk about data liquidity, it's invariable, all of us, and I was doing clinical research as well, data is invariably in clinical silos of some sort. And one of the things that we have worked hard to provide is all sorts of ways of getting data onto the cloud. And whether it's things like using Firehose, Kinesis, data sync, secure FTP, and of course in healthcare, the fast healthcare interoperability resource FHIR. These are all different tools that we've provided. In fact, the FHIR resource is an open source resource. If you go to GitHub, you can download that. And it really provides you an easy way to create basically a FHIR endpoint to create this interoperability layer to be able to move data either from disparate systems or even sometimes from legacy places where data is all locked up. into your sort of data lake. Now, the thing about data in healthcare that would be used for research is that it's not always discrete. It would be nice if all data was discrete and quantum, but most of the time, data in healthcare is actually tied up in clinical notes. And so when you talk about doing research, the challenge that we often face, and our customers and our partners come to us and say, look, the data is unstructured. And if I'm going to do some sort of research and build machine learning models that do predictions and accelerate discoveries, how do I handle? Can you help us actually break down these unstructured reports into something that can be used for building machine learning models or doing clinical research? And so Amazon Comprehend Medical is this tool set that actually reads the notes and breaks it down into knowledge graphs. And if you think back in high school, when you might be reading a book and you highlight keywords, it's a metaphor that might help, but it's of course not just keyword extraction, it's actually knowledge graph. So if you extract a keyword that is a medication, your model will understand that the medication, here's the dose, here's the route, here's the frequency, here's potentially the side effects that are in this clinical note. And so that is another way of helping to liquidate the data that will help accelerate research, and we'll get to that in a second. And of course, one of the things that most folks want is it's not just, you're not just doing work in one organization, you're probably coordinating amongst many, which means you really want to move to some sort of normal ontology. And so Comprehend Medical will also allow you to move to ICD-10, RxNorm, and move it to SNOMED, so that you can actually collaborate amongst one another and use a normal ontology that helps you sort of do that work together. And then of course, it's not infrequent that when you're doing work together, you might have to strip out the parts that identifies an individual, the protected health information. And so this tool also lets you strip out that data. And I'll mention later on, we'll talk about in Canada where Vancouver General Hospital was doing a COVID collaboration. And when they were bringing data from all over the world, they were using this to strip out the data so they could combine it and build a prediction model for COVID on CT scans. And so that's sort of the textual piece. Now, when we take a view of data in healthcare, if you broaden your lens, it's not just textual data, even if it is notes. There is voice data. And so Transcribe Medical, for example, will help you take that from voice to text, and then you can daisy chain it from text using Comprehend Medical to knowledge graphs to ontologies, and then strip out the PHI and then collaborate. And then beyond voice, there is, gosh, unfortunately, so much still a PDF and faxes. And so you could use TextRact to be able to intelligently extract that and liquidate the data that's tied up in those documents. And then there are images. And so Amazon Recognition allows you to actually build models and extract information from images as well. So when you sort of take this slide as a whole and think that if you are doing work that you have data that's tied up, and we know that as you want to accelerate any kind of work, whether it's basic science work, whether it's clinical bedside work, that you often are faced with this frustration, the data is tied up. And so all these services are ways of getting that data liquidated and moved into an environment where then you can do things with it, like applying machine learning. And in fact, on this slide, let me just walk you through Vancouver General Hospital in Canada, where back in, it was March, where they wanted to build a prediction model for diagnosing COVID on CT scan. We all know the ground glass appearance, but they wanted to be able to use that as a way of helping a radiologist elevate the suspicion of COVID. And so what they did, in fact, actually, there's one other piece that will come to say, what they did is they took their own imaging data and used Comprehend Medical to strip out the DICOM header and de-identify the patient information. So it's de-identified, move the data using Amazon Image Recognition to build a model. And then what they wanted to do is actually build data from all over the world. And so we helped connect them to South Korea, Singapore, other parts of Canada, United States, different entities. And that data was brought in as well. And because they only had a few hundred cases of their own, and we wanted to help them build strength in a machine learning model. And so we're using our open data registry and data exchange from across the world, all the data that Vancouver General Hospital already had partners that they collaborated with. And so they were able to use the same methodology of liquidating the data, de-identifying it, and then bringing it into a common data lake from across the world. And they also brought clinical notes, because your machine learning model is stronger if you include the clinical notes. And so then they use Comprehend Medical to take those clinical notes from all the world, which happened to be English. They could only use the ones that were English for that particular study. And then they use Comprehend Medical to take those notes into their knowledge graphs. And so when you look at this slide, this embodies essentially what University of British Columbia in Canada did, which is use data from all over the world and their own. They used image recognition. They used Comprehend Medical to liquidate the data, to build a knowledge graph, to de-identify the information, put it onto a data lake, build a machine learning model that when a CT scan is brought in, it can give you a predictive probability, of this individual having COVID. And this was repeated again with chest X-ray with UCSD, University of California, San Diego. So this, we started by saying we wanted to talk about data liquidity. I gave you an example of research as well, but let's now tilt in a little bit more. So far we said, we want to do research, we want to accelerate it, and we need ways of liquidating data. And then now we want to use that data, because the whole point is, how do you actually derive insights and accelerate? So let's talk about a really great example. And again, it's this one I think is related to COVID, which is AbCellera. Now, AbCellera is a young biotech company, and their mental model is that, as clinicians on the call, you certainly will appreciate this, is that we in our bodies, when we recover from an illness, we make the necessary antibodies to treat whatever it was, which is why we recovered. We probably make hundreds of trillions of different kinds of antibodies or opportunities for antibodies. And so their mental model is, if we can isolate that antibody, if they can isolate that antibody, then they can create therapies based on what the bodies create itself. And so in early March, in January, they got their hands on the plasma of a patient that had recovered from COVID. And so what they did is they spun out all the B cells, all the immune cells. And AbCellera has a particular microfluidic technique where they're able to, they actually apply tagging to identify cells that are producing antibodies. And then they do whole cell imaging. Now, if you've ever done whole cell imaging, it's actually a lot of space to look at. It's not quite like electron microscopy, but it's a lot of ground. So you and I couldn't necessarily sit and look at a whole cell under the microscope, especially 5.8 million of them. But that's what they did. But the way they did it is that they used machine vision. Some of those services I talked about earlier, where they did the whole cell tagging using microfluidics, and then they took images of the whole cell, that 5.8 million whole cell images, and then uploaded that to the cloud. And because of the power of cloud computing, where you're not limited to this computers in your data center, where it's like, okay, well, I can only run certain processes a day. So if I do the math, this might take 16 months to run through all these. In the cloud environment, you can spin up as much computing power as you need. There's essentially practically infinite compute power and storage. And so you can rev that up, and you only pay for what you use. So it's not like the legacy concept where you have to order equipment, wait till it's derived, you put it in a data center, you wait till IT wires it up and connects it. You simply dial up whatever you need. And so they look through 5.8 million B cells in 3 days to identify the 2,200 cells that were producing antibodies in 3 days. This is not a task that can be done by either manual review or on-premise computing review. So once they did that, then they broke those cells apart and sequenced all the DNA of the ones that were producing the antibodies themselves, the region of the antibodies that were being produced. And that, again, to sequence all those DNA, if you think of how long it took to sequence the DNA in the past, I think it was like 12 years for the first whole genome sequence. Again, applying computing power, they were able to sequence all of those cells and the DNAs within the next 3 days. So 3 days to identify, and then 3 days to break all those apart and identify the 500 antibodies that appear to be interacting with various proteins on SARS-CoV-2 virus. And then from there, they narrowed it down to 24 favorable. Now, as a biotech company, their secret sauce is they understand what kinds of the DNA sequence and antibody properties are amenable to being produced in the lab. So that's really their so their secret sauce. So after doing the sequencing in the next few days, they identified the 24 that had favorable characteristics that are likely to be able to be made at mass scale and to be transported at room temperature and so on. And from all of that, they narrowed it down ultimately to one antibody in one cell line that matched the spike protein for SARS-CoV-2. The whole process from beginning to end took 6 weeks. And so from the time the bag of plasma arrived to the time they had a candidate cell line that, as you might know from public press, AbCellera then partnered with Lilly to then take that to production, to clinical trials. So from bag of plasma to commencement of the cell line and going to clinical trials was 6 weeks. This is the kind of compression that can happen when you apply, A, when you liquidate your data so that it's not a manual process. B is when you apply computing power to be able to do things that normally would take months, years, to be able to dial up the power and do things. It's like water. You can have drip of water, and then if you need a lot of water to fill a glass really fast, you just turn on. You don't go getting new plumbing and have more drips of water. You just turn it up, fill the cup, and turn it on. And that's what they did, which is how they took that to clinical trial within 6 weeks. So that's a really good example of accelerating and using machine learning. Now, one thing you might ask is exactly what is machine learning? And what do you really mean when you talk about doing that? So let's just give you one slide of what it is and demystify this idea of AI and ML. And the example I'm going to give, I'll use a clinical one again, but here's the example I'm going to give you. If this image here represents you and I, where we have information coming into us, and let me see, I have actually a slide. Yeah, here, information coming to us. Assume that gear is our brain, and information comes to us, and through our training, we decide something, yes or no. So if I showed you an MRI, CT, excuse me, and if I had trained you that, look, air is, Hounsfield units is less than 1,000, fat minus 50 to minus 100, water is 0, white matter is this, and so on. And so if you've trained this and you look at a CT scan, you can, based on your training, decide this is air, this is bone, this is blood, this is white matter, this is water, this is fat. So that's you, that image in the top left, metaphorically. So with machine learning, it's the other way around. What we do is we give a machine the data, and then we label the data. We say, so the same CT scan, we give the CT scan to the computer, and we say, that's bone, that's air. We don't tell the Hounsfield units. You don't need to. Again, I'm using this as a metaphor example. You just say, that's bone, that's air. You repeat this over and over and over again. That's bone, that's air, that's blood, that's blood. It's called labeling. And then the machine builds an algorithm, a model. That model you can take elsewhere and then give that model data that was never in the training set. And it can make a decision, what's bone, what's air, not by a if-then, but by this model, whether it's a neural network or some sort of a model. So if you look at the image in the bottom right, it's reminiscent of what you and I do in the top left, which is why people call artificial intelligence. Again, I'm trying to oversimplify, so forgive me. If those of you in the call are machine learning experts, you're like, well, there are a lot more details here, and I get that, but I'm trying to simplify. So you take data and you label it, the bottom left, you say, this is bone, this is air, or this is a cat, this is a dog, this is a tricycle, this is a bicycle, builds a model, take that model, and then you give it data it's never seen before, and it can make those decisions for you. It can give you those probabilities. Let's look at a real life example with clinical. The work here we did is with Cerner. Now with Cerner, as you probably know, it's a large electronic health record. Oops, I repeated that, sorry. That image is, okay. With Cerner, which is a large electronic health record company, they moved their longitudinal patient records to AWS, about 200 million individuals, their longitudinal record. And what we did together, and this is published in a peer-reviewed publication, what we did together is took the data and labeled the patients, took 210,000 records, de-identified, and labeled the patients that had congestive heart failure. So we said, this one has congestive heart failure, that one has congestive, and the model began to be trained on congestive heart failure. And this was 210,000 patients that were used to train it. Then we brought 3,000 records the model had never seen before. that had developed congestive heart failure already. So we knew that they had congestive heart failure. And we told the model, tell me if this patient is going to get CHF or not. And the model could predict which patient is going to get congestive heart failure 15 months prior to onset. That means that, and the area under the curve accuracy was 0.915. So for those of you who do this for a living, that AUC of 0.915 is pretty darn accurate. That means that when a patient arrives in the emergency department, the model can look at the last 12 months of data, and it can predict with 0.915 area under the curve accuracy if this patient is going to have CHF in the next 15 months. And so when you think of machine learning and artificial intelligence, it's a tool that will be what EHR companies are doing, and Cerner has announced this publicly, is to embed these atomic intelligence directly into workflow. And so as you are using the electronic health record, these are essentially digital tests that will provide you with additional insights. So you order a CBC, electrolytes, you might order MRI, CT scan, and someday you're going to order these digital algorithms. Just as you use input from MR, CT, lab tests to make a clinical decision, you'll have one more data point, because there's a lot of hype out there on, oh, AI ML is going to replace physicians. What we see happening, what customers are doing, is using these tools as another tool in the tool belt for clinicians to make decisions. So for example, this is another example. It was Oklahoma State University Center for Health System Innovation wanted to help clinicians triage. You can imagine, well, in many parts of the world still, but certainly this is back in March. They wanted to provide input so the clinicians could have more data as they triage the sick patients that were coming in. And so they built a model that looked at simply data on admission. Simply data. In other words, you've just taken a history, medical history, you've done some lab tests, and you just look at that admission data, and it could predict with 75% accuracy which patients were likely to die from that COVID who arrived in the emergency department. And then they want to see if they can make the model better, but still be very efficient. So they added one more day of data. So they added the data that were acquired in hospital at the end of day one to the model. And then they were able to improve that by about 5%. So again, this is data that helps the clinician in the triaging process. It's not making a decision, but it's helping. And these are, when we talk about data liquidity, when we talk about breaking down silos to use those for accelerating decision-making research, or whether it's in this case clinical, this is an example, and the machine learning model is some of the examples. Now, you may say, okay, so how? Let me just, having said this, I gave an example of Vancouver General Hospital. Actually, that one was led by a radiology resident with a head of CT, chest imaging, Dr. Nicolau, Savas Nicolau. So we are talking about individuals and teams that are in hospitals, that are in clinicians. So this is, you might think, well, gosh, do I need to have a PhD in mathematics to do this? What would it take? And so let me tell you about the how. And the how, on AWS at least, the how, we have three tiers of helping you do machine learning. And tier one is for those machine learning professionals. These are the individuals that like the command prompt. They immediately bring up a command prompt and are hitting the command prompt. This is where you want to roll your sleeves up and you want to pick the protocols, pick the frameworks, build the machines from scratch and do it. We certainly can do that. Typically, I find those clinical environments where folks are doing, unless they have data scientists, machine learning professionals on the team, this is an area where most don't need to go to in a clinical environment, but you can certainly go down to that level, run the PyTorch or the Jupyter notebooks and run PyTorch or Cafe or what have you, and use different kinds of glue-on interfaces and so on. The part where I see the clinical teams most often is in this other tier, where we have it's an integrated development environment. It's called SageMaker Studio. And the studio is the more sort of point and click type, where you click, point, and it gives you suggestions. It says you may say, well, look, I'm about to embark on a thing where I want to accelerate computer vision and machine learning through that. So you pick a pre-made selection there. It gives you options that way. So you point to it, it gives you pre-configured setups, You point to your training data set, it trains it, and then you can deploy it. So in fact, the example I gave for Vancouver General Hospital, they use SageMaker Studio and loaded them and made their model. The University of California, San Diego built their chest X-ray model in 10 days using SageMaker Studio with 2,200 chest X-rays. And then, of course, there's another tier, which if you're a software engineer and you want to use machine learning, there's a whole other tier of using APIs. And so these are sort of 3 tiers. So I point this out because often people think that it's a bridge too far, that this is, you need to have a team of PhD scientists. It would help, but it's not. You should feel comfortable engaging and trying different things because, and the beauty, of course, I shared with you earlier, that this is the whole model in the cloud, in any cloud, is you only pay for what you use. When I was doing research, there was always the light version of a software that was like, let's say $1,000. And then there was the professional version of software for analysis that might have been like $7,000 or $20,000. And the challenge was that as a young researcher, I could only afford the light version and I didn't have all the features that I wanted. Cloud is different. You get all the features, but you only pay for what you use. And so you should lean in if you want to experiment and try, because it's literally like electricity. You turn on it, you pay for electricity use, you turn it off, you're done. All these tools are available to you on the cloud, and you just try things, experiment, and you might only incur like 15, if it's in the US, $15 of usage. All right, so that's it.
So actually, I think it's very, good timing. So we also have Prof. Stoyanov here from UCL, machine learning expert, computer science background, heads up everything in terms of robotics and imaging. Prof. Stoyanov, what have you thought so far on Shez's presentation? Any comments, thoughts?
No, I think it's fantastic and really, really exciting to see these tools being built that can generalize across different applications. We're looking at generic views of imaging data or metadata or health record data. And, to do that in a way that generalizes and scales, and to deploy that in kind of cloud infrastructure that can link to different hospitals, you really need huge amounts of resources. And so it's great to see, AWS and others investing in this space and really innovating, and also allowing others to innovate with their technology. So really exciting stuff.
Absolutely. Shez, we thank you very much for your presentation. Completely immense work that you're doing from Amazon. Are you able to stay? Because what we wanted to do is have a kind of joint panel discussion after Prof. Stoyanov's talk.
I can stay unless I get. Yes, I will stay as long as I can. I certainly want to also. Yes, let's carry on.
Yeah, I agree. We have some exciting questions lined up for Dr. Chez as well from our audience, as well as social media platforms, so we can keep them as part of the end panel discussion.
Absolutely. Faisal, do you want to introduce our next guest?
Absolutely. So once again, welcome, and we move forward with our next talk, which is by Professor Danail Stoyanov, who's the director of Wellcome, as well as the EPSRC Center for Interventional and Surgical Sciences. He's also a professor of Robot Vision, Department of Computer Science, as well as the Faculty of Engineering Science at UCL. We're absolutely thrilled to have you and share these experiences and insights in the field of machine learning, computer science, and clinician engineering as a whole. The stage is yours, Professor Stoyanov.
Thank you very much. It's a great pleasure to be here and to be able to speak to all of you. So far, it's been a really exciting program over the last few days. So thank you very much for this opportunity to talk about some of the work that we're doing at UCL, and also that is being commercialized through 2 companies where I'm particularly involved. One is Digital Surgery Limited, which is now part of Medtronic, and also Odin Vision, which is a UCL spin out. So I'll predominantly focus my talk around computer vision in surgical images. And the reason for that is that digital cameras, are now present in the majority of modern operating rooms. So we see, surgical robots that may hold a laparoscope, and that could be a camera that delivers a single or a stereo or even a trinocular view of the operating field. These devices could be flexible, they could be held by microscopes, or they could even be swallowable, such as pill cams, where you essentially use the device to travel through the GI tract and capture diagnostic information, which is then a perfect data modality to use with AI, because you don't want to look through 8 hours of video of this capsule traveling through the body. Ideally, you want to highlight the very, very important bits and just investigate those. And that's the sort of problem that AI is very good at solving today. So data that's captured in modern operating rooms can take a variety of forms. These are just some examples from microscopes in neurosurgery and cataract surgery, and also laparoscopes and endoscopes in abdominal surgery. And I would say that this is probably one of the largest unstructured, underutilized data sets in modern hospitals, because this is a huge amount of information that's recorded in all procedures. The video is inherently present because that's what the surgeon or interventionalist uses in order to perform the procedure. But for the most part, it's either never recorded, or if it's recorded, it's usually discarded after a period of time. And yet, this information contains a lot of data around what happened during a procedure, what events occurred, potentially pathological information about the appearance of certain diseases and how that appearance may vary across different patient demographics. It may also contain information that we're just not attuned to noticing just yet, but could be really, really interesting for us to interrogate and capture using AI systems. So we've been building algorithms to take advantage of information like this for a very long time now. And I'll try to just blitz through over the next 20 minutes or so through some of the directions that we have explored in terms of leveraging surgical video data and how that may lead to potentially useful clinical solutions. So the data domain really is very large, and we can explore it in a variety of different directions. The three that I'll focus on today are really the semantic domain, which is essentially understanding high-level labels of what is in the image or in the video. Is it an organ? Is it an instrument? Sort of spatial labels about what the image contains. I'll talk a bit about the temporal domain, or the spatiotemporal domain, which encodes activity, workflows, events that may occur during a procedure, and also about the spatial domain. And I'll start with the spatial domain, which really refers to understanding space and geometry and understanding the 3D shape of the surgical site. So I'll show some work here on how we can use images to infer depth and to infer motion from the surgical site. So these are some videos of robotic lung surgery, and we're using the video camera in order to estimate how far away structures are from the camera. That's the gray image you see on the bottom left. And also to estimate how structures move in 3D. And that's the colored image that you see moving. The color gives you an orientation in terms of the direction of the motion, and the intensity of the color is the size of the motion. So we can essentially use algorithms to turn our standard imaging modality during surgery into a spatial measurement device. And this is the same technology as what is being used in autonomous vehicles. So sensors mapped, essentially used to map the environment. We can link this mapping information over time. So as the camera moves, we can start building a much wider map of what the environment looks like. And on the right, you see a video of a stereolaparoscope moving in robotic prostate surgery. And you can see as it moves around, you can see the pelvic bone at the top of the prostate. And so essentially you're kind of linking this information that the camera observes over time in order to build a detailed, dense understanding of the anatomical site. And I should say that this is really the only way to understand 3D space during surgery, because we don't have any other sensors. Of course, you could engineer technology to solve this problem by other means, but that may involve inserting new sensors or different cameras or being more invasive. Whereas by using vision, you're inherently using the data that's available in all surgical procedures, or the majority of surgical procedures nowadays. The reason why, excuse me, the reason why understanding 3D space is important is that we can potentially use this information to build navigation systems. So in this video on the left, you're seeing how our ability to map where the camera is and the 3D geometry of the surgical site is allowing us to register a preoperative model of the patient anatomy. So you see this pelvic bone and the prostate, and you can overlay this information onto the video, onto the intraoperative video, and maintain the alignment as you move the camera. So you're essentially providing augmented reality visualization during the surgical procedure. You could actually take this a step further and actually use the information about motion, so how structures are moving in the surgical site, to deform these organs. So this is an example of nice work done by a team in Strasbourg, where a finite element mesh of the liver is updated, so deformed, to align with the intraoperative anatomy. So as organs are deformed, we can potentially use the visual information in order to update the position and the location of these tomographic models that can be overlaid. So this is in essence potentially allowing us the ability to provide better navigation systems. Now, a particular procedure that we're investigating more recently is providing navigation assistance in endoscopy or in endoscopic investigative procedures. In this case, you only have a monocular camera, so extracting 3D depth is much more difficult. So we were embarking on this 4-year project called EndoMapper with 3 computer vision teams in Europe, really looking at how we start building entire maps of the colon environment purely from the endoscopic image. And because we don't have any labels, I think in a previous talk we saw the importance of structuring data and labeling data in order to train AI systems. But with vision in surgery, those labels are missing. And because we don't have labels to perform the mapping, we can essentially try to approach this problem from a unsupervised or weakly supervised manner. So in this case, we're using simulation. We take a CT scan of the patient's colon. We can fly infinite amounts of fly-throughs, so infinite amounts of endoscopic procedures in this virtual model in the virtual environment. We train the AI system to predict depth or to predict shape in this virtual setting. And then we can transfer that model with generative adversarial networks in order to work in the real endoscopic environment. So this is an example of a real colonoscopy where we're using the monocular endoscope to estimate depth. Now, of course, this is still preliminary work, and we are yet to start linking these time instant depth measurement, and that's really the next challenge that we'll be addressing over the coming years. But still really exciting to be able to see that we can now turn a monocular camera into a depth or 3D geometry sensor, which is really, really exciting and only been possible in the last few years. Now, in addition to understanding the full 3D geometry of the surgical site, we might also want to understand space in the sense of enhancing the field of view of the surgical camera. In some procedures, for example, in utero procedures, the camera is so small that the field of view is extremely narrow. And so localizing targets in a wider context, for example, localizing all the blood vessels on the placenta in order to photocoagulate them, can be really, really challenging. Now, we know mosaicing technology or panorama technology works very effectively on our mobile phones, but unfortunately, it doesn't appear to work that way in clinical problems or in surgical problems. So we've been developing mosaicing and panoramic mapping techniques for this particular environment. And I'll show an example of our most recent work where we essentially achieve the mapping by segmenting the fetoscopic image into vessel maps. So estimate each location of a blood vessel in the image, and then we use those blood vessel blood vessel images in order to achieve the final mosaic. And you can see how the vessels align nicely on the right. And I'll just show this on a realistic video so that you can see how this new way of approaching the problem means that the alignment between the different images is much, much nicer than in a conventional panoramic technique where you get a lot of drift and misalignment between the vessels. So we predict where the vessels are, and then we use that in order to achieve our wide field view of the surgical site or our mosaic. So really excited about taking this technology to theater, and I'm hoping that we'll start doing that probably sometime in 2021 at UCLH. So I've spoken a little bit about the spatial domain. And now I'll talk a little about the semantic domain. So in the semantic domain, we take an image from the surgical site, and we'd like to assign high-level labels to the different regions within the image that can be identifying different organs or different substructures within an organ, potentially instrumentation, and so forth. So meaningful spatial labels obtained purely from the image. So this is a problem called semantic segmentation, and here you see an example of a semantic segmentation AI model running over a robotic surgery procedure. So you take the video input from the left image and you obtain high-level labels identifying which part of the image is occupied by a kidney, which part of the image is occupied by an instrument, by the shaft of the instrument, by the by the tip of the instrument, and so forth. This is quite useful in terms of building a high-level understanding of both activity, also of the spatial location and the spatial labels of where things are, and really is important for us to build both navigation and information extraction systems. The main challenge for this in surgery is that, again, supervised training of this type of model is very limited by the amount of available data. So this is an example trained on only about 400 images, which is very, very small for computer vision models. And this was data that was released by Intuitive Surgical about 3.5 years ago. So only 400 images. That's a very small sized data set. This year, we released the data set as part of MICI, which is about 10 times larger. It's still very small compared to standard computer vision data sets, but still much, much larger than what was previously available. So this is an example of a semantic segmentation algorithm running over a cataract video. And you can see extremely fine level detail being identified in the high meta label image that we can extract from the raw video. So we can identify the different anatomical structures as well as the instrumentation, and this data is now available for the community. So in addition to full semantic labels from the surgical site, a lot of effort has gone into understanding the location and the activity that instruments are performing during surgery. The reason for that is that you can link this to a robotic control system. You can link instrument motion to skill and to proficiency. You can link instrument motion to activity in order to provide reporting. So instruments are of particular interest in terms of building models that can extract this information from the video. And in this particular example, we're just showing how vision can be used not only to detect where the instrument is, but also to detect the articulation points. So you're getting a really fine-grained nuance of what the instruments are doing. And this is not using the robot kinematics at all. This is purely based on vision. Now, one challenge with this type of model is that once again, it's reliant on data. And to bypass this reliance on data, we're now investigating how we might use, once again, simulation environments, but also the robot itself. So we're fortunate enough to have Da Vinci research systems in our lab, and we can forward drive where the robot instruments are. That means that we've got very precise knowledge that allows us to build high dimensionality data sets that have the robot kinematics So full labels of where instruments are, and then we can train the AI models on this type of data without any human level interaction. And I think that's where the field is going to be going over the next couple of years, because there's no way that we scale this into the millions of images by manually annotating each image in that way.
Absolutely.
Now, another area where this type of technology is really important, so semantic segmentation, is in endoscopy. So a number of systems are now commercially available to detect the location of colonic polyps, potentially to characterize them as well. I'm giving an example here of a system that's available through a UCL spinout that we founded, Odin Vision. So this is now a CE marked product, and we're continually evolving this technology to provide better and better predictions. So in essence, you take the endoscopic video, and rather than extracting high-level meta-information, you're extracting a pathologically meaningful information. So you're detecting the polyps, and you're potentially characterizing what those polyps are, and that has a number of potential advantages. And this is now going into clinical trials throughout a number of NHS hospitals. It's also part of the NHS Accelerator program. So really exciting to see AI from the lab into the clinical environment. Now, the next models that are being developed by Odin are for upper GI. So the same approach as for colonoscopy is also can be used in upper GI procedures, and this is an example of a system that has recently been tested once again at UCLH, and you're seeing how you can characterize these plastic lesions, these plastic parts of the endoscopic image very, very effectively, and I'm sure that this will also be an available product.
Well, thank you so much, Professor Stoyanov. I'm just as fascinated by your presentation, and I'm afraid because of the strict time frame that we're following, we have to hold it to here. But now we're open to our panel discussion, and perhaps we can have Dr. Shez come on board as well for our questions and discussions on a larger scale topic of data integration, machine learning, and surgical applications as well.
Absolutely. I just wanted to say we have, I think, the kings or the giants of machine learning here, so Amazon and UCL. So really very incredible work. And my background is in gastroenterology. Lady Catherine, she's based at the Cleveland Clinic, also in GI. And anything that you guys do that makes colonoscopy easier, you know, it's very welcome. So I was actually also seeing that Amazon is now delivering the capsule endoscopes to people's homes. So incredible stuff that's happening in endoscopy generally. So Faisal, Lady Catherine, do you want to lead the discussion?
Sure. So, well, thank you both so much for making it to the conference. Definitely having you both gives us a very nice perspective of what's happening, of the basics. So thank you for doing that. Maheen has a question to start with. Well, she would love to know where you see AI and machine learning fitting in the healthcare landscape of resource-limited countries. Any success stories you can have that you can share?
Is it a particular question to a particular person, or did you want Dan and I both comment on that?
Whoever wants to start, that's fine.
Sure. Well, you know, one of the advantages, the advantage of cloud technologies, of course, it is global. We have, there's access, if you will, across the world, wherever there's a connection to the internet. Now, notwithstanding if there's no internet connection, there's some solutions to that as well. So I'm going to put that aside for a second. I'm going to at least assume there's an internet connection. And the advantage of actually using cloud technology is that it actually is a bit of a great equalizer, because particularly the way in which cloud and computing in the cloud is used, where you're only, if you will, paying for what you use. So that's one of the methods in which it actually is an enabler. Now, on the other hand, there are some places where there's even more challenge for even funding basic utilization. And in fact, a good example would be with COVID, where we wanted to help accelerate research across the world, and AWS committed $20 million dedicated to exactly that, to underserved countries and young researchers with limited resources. And so in addition, so I would say that there's two ways of looking at this. One is the foundation of cloud technology, where you're only paying for what you use, means that you actually can experiment with very little cost. And AWS and Amazon has leaned in areas like just this year, excuse me, I'm already in 2021. This year, we actually had committed to actually fund fund organizations that are trying to do things but are under-resourced and understaffed and underfunded. So those are the two ways we've seen it. There's a different challenge for disconnected states, but I'm going to stop there and we can talk about disconnected if needed. But those are the two ways which I would say that we've leaned in.
From a more academic perspective, I think what we've been exploring is how we might be able to use AI to deliver expertise in areas where it may not be available. So we've got one project led by University of Leeds, where we developed the AI component in collaboration with Tianjin University in China to look at deploying endoscopic solutions for rural China, so outside of the big cities. Also with Odin Vision, we've been looking at, actually this is work funded by the European and UK space agencies, the use of satellite technology to be able to deploy AI models again in rural settings. So I think there are great opportunities for kind of delivering expertise in areas or in locations, geographical locations where it may not normally be available. And I think there's other use cases with telepresence potentially, or telementoring, teletraining. So I think there are loads of exciting possibilities there as well.
Well, there's a lot of exciting work ahead, definitely, and just bearing in mind that the needs of different countries are slightly different, and having a bit of a sense of what the needs are, it's also very important. Now, from a clinical perspective, well, I feel that sometimes, particularly coming from the endoscopic world, as you're saying, there's sometimes when we barely take any pictures at all in the procedure. So I think we could do a better job of that. One thing that has happened is that even if we want to make a video, sometimes it takes such space that there's really no place that we can gather that information. So I'm just wondering, from a clinician perspective, what can we do to help build a more robust database with the tools that we have? How we can optimize what we have in order to help out build all of these robust databases, not only from the gastro perspective, but from overall fields.
I mean, I would say that better tools are coming your way very shortly. So, you know, I think it's a very practical problem, but it's a real problem that clinicians rarely have the time to manage many USB sticks, upload data here and there, and then label it and so forth. It's not that it's not possible, it's just that time doesn't allow you to do it. And also the incentive for doing it is you know, not so great. So I think over the last few years, we've reached a technological maturity where there is an incentive for the companies to deliver better solutions to be able to manage that process, and potentially then to have an incentive because you get a service out of it. You either get some analysis or you get some added value to your practice or to your capabilities through using technology like that. So I think it's coming. That's what I would say.
Yeah, I think that's you know, exactly, it's a real problem. The large data sets are a true challenge. In fact, whether it's video, medical imaging, including pathology, genomics, these are all areas in which we're leaning in. And a good example is the work we're doing with Philips, where it's around how do you get, and that's around medical imaging. How do you get, we have a device called an Outpost, and Outpost allows you to bring the cloud to your data center. And so this is one way in which we're trying to help solve that problem, where you actually extend the cloud to your data center and you can actually put the images on this local device that then slowly streams it back to the cloud. So it's available for machine learning, building and models. So you're actually putting your finger on a problem that is definitely well recognized. And in our space on the AWS side, we're working, as Dan mentioned, we're working with other companies that are building solutions to Dan's point, that's going to come to you that will be able to store essentially infinite amount of data. And in fact, the last thing I'll mention is that there's an implied problem there as well, which is cost, because there is the actual data storage. In other words, having low latency for data storage, and that's one problem, the latency of how can I put this and quickly, and my system isn't slow. And then as you store more and more, I've never met a researcher or a clinician that said, you can delete last week's data. I've never met a clinician. And so one of the examples where we're working on, and we have now, is that you have different tiers of data. For example, there's the active use data, which is a certain price point. And then there's Glacier, which is a data type we have, which is, it goes in and it's less expensive, but maybe not as quickly available. And then there's Deep Glacier, which is like ridiculously inexpensive. And so what happens is that we're seeing companies like Philips use that to have sort of active storage that is highly active and being used. And then if it's not being used, automatically goes to Glacier, where it's less expensive. And if it's not being used for a long time, it goes to Deep Glacier. And so the cost goes down. So we recognize not only latency and access, but actual cost. So we're working on those, as we mentioned. Hopefully it'll be coming your way through companies like Philips, like ones we've heard today.
Absolutely.
I'll just add that, you know, cost is critical, because if you expect the hospital to pay for storing all the data, which is sometimes, you know, from a pure scientific perspective, I would love that. But then the hospital may come back and say, well, that is doing that versus, you know, allowing this and that treatment for somebody. And so these are hard choices. And I think, you know, there's no point in storing data infinitely if you never ever use it in any meaningful way. And so I think it's that sort of nice synergy between being able to utilize, in my case, you know, video is what I love. So being able to utilize the video may give you the incentive to actually start storing it. And then maybe you have the ability to refine it, to store it in a low cost way, and so forth and so forth.
Right. No, this is exciting stuff, like you mentioned. And I mean, even though as clinicians we might be busy, but I think it's the busy, excited part that we're looking forward to. My question here is really more about how the two main challenges that we see, at least in the research side of data computing and analysis, is accessibility and standardization of this data. So especially with the different, I mean, on my side, it's 3 to 4 different electronic medical records being implemented in various hospitals around. So that challenge of standardizing this data comes in. And then there's the accessibility of collaborating with enough institutions to give the results that we need. So how have your institutions, from your perspectives, helped to give us some solutions and positives to these two challenges that we have?
Maybe I'll just briefly mention, you know, in the presentation I was referencing a few different, we recognize that's a challenge. In fact, there's not a single research organization or clinical organization we've talked to who has not pointed out that data liquidity and interoperability as a problem, which is why we built some of these turnkey services that you can use to go from text to knowledge graph to ontology, like ICD-10, RxNorm, SNOMED, because we recognize that that's the tier that you need to get to be able to collaborate. And so I would point to, if you wish to experiment there and try things out, I'd point you to the one service we have, which is called Amazon Comprehend Medical, which really will help you pull that data. Well, start with Fireworks. Fireworks is an open source code that we have that allows you to pull the data out of an EHR using Fire, which most EHRs today should respect Fire APIs. And then once you pull that data out, if it's discrete, then great, you can take it forward to codes. If it's in clinical notes, you can apply Comprehend Medical to break it down into discrete, and then to take that to notes and even de-identify. So we've tried to provide the tool sets that allows you to create a pipeline to go from your EHR to what is your holy grail of a data lake that's ready for either labeling or for just research. So that's a problem space we've been in, and I would point you to some of the services we have. And I'd love to hear, I know that in video it's a little bit different. And so, but certainly for textual, you mentioned EHRs, I think we've got well-treaded path that in the presentation, and certainly if you go and look at Comprehend Medical, that will provide you with what you need to do that.
Absolutely. Well, thanks very much, Shez and Prof. Nan. Fantastic discussion. I wonder if you wanted to stay, because whenever there's the kings of engineering, we always have to invite the queen of engineering. So I think Joe is available from Google Health. Joe, can you hear us? Hopefully. Can you hear us, Joe?
Can you hear me now?
Yeah, perfect.
Okay, perfect. Sorry.
Okay, fantastic. Perfect timing.
Hello, everybody.
You've probably been listening to all this great discussion from industry and academia from the king. So now, obviously, we have the queen. So Faisal, do you want to do the introduction? And Prof. Dan and Shez, please stay if you have time.
Right. Thank you so much. And I'm really pleased to move forward with our next talk for the day and introducing Dr. Joanna Chwastowska, who is an engineering lead at Google Health. And she has pioneered the field of technology and software engineering by leading various initiatives as well as startups in different industries, including Google's DeepMind Health team. And in really bringing together artificial intelligence, digital transformation, and various other aspects of how clinician engineering can also come together, we're very pleased to have you with us today. The stage is yours. Feel free to share your screen as well.
Thank you so much. Let me start with the screen sharing, because that's always the most exciting moment of every presentation.
Exactly.
But let's hope that this works. Can you see the slides?
Yeah, absolutely.
Perfect. Okay, so welcome everyone. My name is Joanna Chwastowska. I'm an engineering lead on the Google Health team in London. And today I would want to share with you like the brief overview of Google Health and what we are doing and why we are doing it. Because Google is quite new in the space, and I think as with everything that the big companies do, it's always interesting to see where the wave is going. So let me start from our mission. As you know, Google's mission is to organize the world's information and to make it universally accessible and useful. And at Google Health, we are thinking of this aspect of bringing all the information sources and making it useful for improving our health. And as we are, committed to improving the lives of as many people as possible, one of the most important areas in which we are striving to do this is health. When you need information about medical conditions, or the directions to the nearest hospital, reminders to take medicines, or help with measuring your fitness progress, you might ask Google for help. And we do our best to provide the most accurate and helpful information across services such as Google Search, Maps, Assistant, Fit, or Wear OS smartwatches. And beyond that, emerging technologies present the opportunities to elevate healthcare for everyone. Today, we are studying the use of artificial intelligence to assist in diagnosis of cancer, predicting patient outcomes, preventing blindness, and much more. And we are exploring ways to improve patient care, including tools that are already being used by clinicians. We are partnering with doctors, nurses, and other healthcare professionals to help improve the care of the patients and the care that you all receive. And probably it's important to start, by stating why healthcare. First of all, healthcare is complicated and it achieves remarkable outcomes, but also it has lots of opportunities for getting better. This is true whether you are looking at the patient's outcomes. One estimate is that 8 million lives are lost per year worldwide because of the lack of access to high quality care. It's also true when you are looking at the costs. In the US, the spend on healthcare is higher than the entire GDP of the UK or of France or of Canada. And there's also a lot that can be done to improve the experience of the providers. So healthcare is the largest employer in the US, but today almost half of the physicians are actually burned out. So there is still plenty that can be done to improve. And that's why we are investing in the 3 main areas of work. Firstly, we make sure that you and everyone else can access the right information and services to improve your health. We are also working on the clinical tools that we built for hospitals and healthcare systems to support clinicians and executives to deliver faster, better care. In the UK, our Streams application is already used by over 1,000 clinicians across Royal Free and Imperial hospitals, which we are super proud of. And we are also working on the spectrum of projects in the imaging and diagnostic space, changing how care can be delivered. The same technology we use in many of our existing products, like Google Photos, can be used to better diagnose people, to improve access to care, to discover new frontiers of medicine and health. And in that space, in the UK, we continue to work towards translating the progress we have made in the AI-based diagnostics of to the clinics that are excited about doubling down on our mammography efforts. Imperial has already been a critical partner on that work. And beyond those 3 core areas that we have since our beginning, year 2020 brought one more for us, that is COVID-19 response. Google Health refocused some of our teams on such efforts as the mobility reports that have been widely used by governments, including the UK, to show the impact of social distancing policies. We've also launched support for COVID labs results in our clinical applications like Streams, COVID-19 knowledge panels, and screeners that are present on Search. And of course, as you likely know, Google and Apple have collaborated on providing the contact tracing solutions that is widely used. So let's take a closer look on some of those areas. First and foremost, for many people, their healthcare journey starts and continues with Google flagship product, Search. And 1 in every 15 searches in Google, so over 7%, is actually health related. You come to us with the wide range of questions, from what causes hiccups to what are lupus symptoms to how to lower your blood pressure. You come to us when you're well and when you are feeling like something is not okay, and when you are managing the condition of yourself or someone close to you on a daily basis. So for that reason, whatever the question is, we aim to deliver accurate, trustworthy, and helpful information. We've worked closely with NHSX to launch hundreds of knowledge panels that drive millions of UK citizens to authoritative content. When you search for, I hope that you can still see the screen. When you search for certain mental health conditions, you are able to actually access clinically validated self-assessments used by healthcare professionals. And this gives everyone the ability to evaluate their conditions, and most importantly, to connect to relevant resources and information and follow up if they are concerned. And of course, your answers are private and secure. Google does not collect or share with what people put in the answers on those screeners or any results of those self-assessments. And you don't only come to Search. You use Google Maps to find the nearest ER or see when your doctor's office open, or you turn to YouTube for videos about healthy recipes or examples of stretches for lower back. You might even be accessing the information on various Google hardware devices. And that's why we will continue to work across the teams and products to improve the information and tools that can help you wherever you are in your healthcare journey. Another important aspect is what we do in the space of the clinical tools. Today, we are providing tools like Streams that are speeding up the detection of issues and treatment of patients. And Streams encourages collaboration amongst clinical teams and supports them to visualize patients' health trends, curate patient lists, spot signs of deterioration earlier, and receive notifications about preventable conditions like acute kidney injury. We are also working on providing clinicians with tools that would enable them to search across a patient's entire electronic healthcare record, pulling together relevant evidence on the patient's condition from multiple sources. In the future, we are exploring how we can help clinicians better organize the complex information they rely to make important care decisions on. And as part of that exploration, we are investigating how artificial intelligence may help medical professionals spot the earlier sign of disease or potential harm. When creating new clinical tools in collaboration with nurses, doctors, and other clinical team members, we recognize that health data is important and sensitive. Our top priority is keeping the data and information secure. We are committed to safekeeping your information with advanced security technology and complying with healthcare industry standards. In that space, we are currently already deploying Streams application in the UK's hospital. It's used on a daily basis at Royal Free Hospitals as well as Imperial hospitals. And we have also announced the next generation set of tools for clinicians, starting with the EHR search, which we are currently testing at Ascension hospitals in the US. And finally, the third very important pillar, probably the most relevant one for the audience today, is around the research, imaging, and diagnostics. And as we speak about that space, it's about a few pillars again. So first would be using the AI to give doctors, for example, the 48 hours head start on life-threatening illness. In this case, acute kidney injury in patients, we can detect it up to 48 hours earlier than it currently is being diagnosed. And this is the demonstration of how AI can accurately predict the condition and let doctors action it faster, avoiding preventable permanent harm to the patients. Next area is in the lung cancer detection. And it's a very promising step forward. This research showed that how artificial intelligence was used to detect 5% more cancer cases while reducing false positive rate by more than 11% compared to unassisted radiologists. The next space would be in the eye disease. And in here, we are using the AI to help doctors address eye diseases. Our research on automated retina disease assessment, called ARDA, showed how an AI algorithm is helping doctors to quickly spot diabetic retinopathy. Our research on optical coherency tomography, OCT scans, shows that our AI system can quickly interpret eye scans from routine clinical practice and correctly recommend how patients should be referred for treatment for over 50 sight-threatening eye diseases as accurately as would world-leading expert doctors do. And there is finally the deep learning for the electronic health records. So as we are going from the space of the imaging and detecting and learning from the images to learning actually from your health history. And in this research, we have showed that how a deep learning model could be used to render an accurate predictions about patients 24 hours after a patient was admitted to the hospital. So in all those spaces, it's important to take into the account not only the breakthroughs in the research itself, but also the translation of the research and how it will be inputted into the live healthcare systems, how it's integrated, how it embeds in the health pathways. And to speak about why we want to apply machine learning to medicine. First, machine learning is really great for use cases where there is a lot of data to look through and where there's a shortage of expertise. And medicine actually have both of those qualities. With the new technology, the amount of data that we as doctors have to shift through in recent years has exploded, especially for screening or routine imaging programs. And also, we have the shortage of doctors globally. That's what you can see on the chart on the right-hand side. This is the shortage of radiologists worldwide. But this is actually true for many other medical specialists as well. And it only gets worse and worse with the increasing incidence of chronic disease like cancer, diabetes, and heart disease. So there is plenty of data to look through, if you think about the radiologists, they would be doing both the screening of the patients, trying to prevent and find the early cases of cancer or other disease to address in the broad population, as well as they would be working on the progress of and treatment of the patients in whom already it has been diagnosed. So let's walk through the example of the application in the cancer diagnosis. Because, you know, as patient gets diagnosed with the breast cancers, doctors often remove the nearby lymph nodes to see the cancer, if the cancer has spread to them. And this also determines how the patient will be treated. So there is a lot of the imaging that is involved in the treatment process. And our AI algorithms was built to predict where the cancer cells are, detect the metastases in lymph nodes biopsies, improve the speed of the diagnosis, and also improve the accuracy of tumor detection. So if we look at the, you know, the needle in a haystack, if we look at those 10 gigapixels per slide kind of data that is being processed, you know, often the lesion can be very small, like really like a needle in a haystack. And the model has been trained to actually help with finding them. Most pathologists, especially under time constraint, can miss a few lesions by when they find cancer. But when they find cancer, they are generally right about finding it. In contrast, the model was trained to find 95 or more % of lesions, but also, you know, it can pick up some of the false positives. So when then we studied the effect of model assistant on pathologist performance for this task, we actually found that the combination of pathologist and the AI model assessing the same scan was more accurate than either alone. And in fact, for very small lesions, the algorithm reduced the rate of false negatives, so the missed cancers, by nearly half. And I think this finding that doctors and algorithms together perform better than either alone is one that, you know, we've seen generalized to other use cases. And for those use cases, this is a promising way of leveraging the strengths of both, like, you know, the clinical professionals, as well as the AI models that can be built and deployed in healthcare to improve the accuracy and reduce any risks in the process of introducing them. And really, you know, to sum up, through focusing on the care, on the core 3 areas of care of our work, exposure of reliable healthcare content in Google products, supporting the clinician and healthcare systems through the clinical tools, and advancing the technology used in detection and treatment of diseases, we ultimately want to help everyone live their healthiest lives. Thank you so much.
No, thank you, Jo. Fantastic. I realize how busy you are at Google Health. So to give the time is really, you know, truly appreciated. If you have time for a few questions before your next meeting, if that's all right.
Yes, sure. That's why I was trying to keep it short and sweet.
That was amazing. Brilliant, brilliant. So we've got Lady Catherine, based in Cleveland, US, Faisal in Dubai, and Luxie, who's based at Imperial. They're going to be leading the questions. So Faisal, do you want to start?
Yes, absolutely. My pleasure. And once again, excellent talk from your side, Joanna. And I think it's inspiring to anyone who's interested in health technology and seeing how much the overlap exists between clinicians and engineering through artificial intelligence. So my first question is really along the lines of how have the team at Google Health really integrated physicians to work with all of these innovations coming in? I understand there must be quite a gap in terms of the understanding between these teams. And so how does the efficiency of such a team work with such diverse backgrounds?
That's a great question, and you know, something I really didn't realize will be that challenging, but also that important when I was joining the team. So I would say let me start from the end. By recognizing how critical it is to have the clinicians, not only clinicians, the regulatory experts, the information governance experts on the team embedded as we develop the software, because a lot of the decisions that you think are nuanced, engineering, optimization details that are being put in the product actually may have the consequence on the clinical safety, on the information safety, ultimately on the clinical decision making in the process of using the product. So I would start from saying, it's critical to have those cross-functional teams. It's critical to find a way to communicate well. And now coming to like how, I would say the communication is probably the most important aspect of it all. Because sometimes when we come from different environments, as you think about it, we may be using even particular terms or words or having the expectations that are unspoken, but we come with those expectations. And then as we come to work as a team, those misunderstandings may really result in huge issues being introduced either to the product or to the team process. So the first step that we took was actually to talk, really like talk a lot, speak to the aspects of our work that might be misunderstood by other side or not understood well, and express what we actually care about. So, and that works both ways. So, we spend hours with our clinicians explaining how they work, how their day looks at the hospital, because, we may have some of the expectations watching TV series, let's say, and that not necessarily is the reality of the hospitals. So they spoke to us about making decisions, sometimes under a heavy time pressure, sometimes being extremely tired, sometimes having incomplete patient record, or being forced to access multiple systems at the same time, being in a life-threatening situation. So we were building that understanding. From the regulatory perspective, I would say, we went beyond quoting the regulatory letter and actually going into the philosophy. What has been the intention of the governing body when introducing that policy? What is the goal of this regulation? How do we make sure that we are not only legal, but actually we are expressing through our product and process that intention and adhere to it? And then, the third side would be the engineering coming into that. And engineers work very differently than people in a hospital, right? Like hospitals are almost like a military units in my brain. They are very hierarchical. There is seniority, there is decision making, because there is people's life at risk, right? So this is super justified. When you think about engineering, it's more of a meritocracy. Everyone can question anyone's opinion, and we'll actually reach some consensus once we debate everything thoroughly, right? So we expressed our side, why it's important for us to understand the why behind what we are building, the how for the clinician, and have the freedom to actually decide how we will build the system to support that need. Because then we can do all the technical trade-offs, right? So I would say I don't think anything can replace that multi-directional conversation and building the understanding. And then the second aspect is really the respect for each other in all that, because there will be misunderstandings. We recognizing that we are coming to that space because we really all want to work on something super meaningful. We all want to help. And sometimes because we want to help so much, we are, at the verge of conflict, because we think our side and considering our aspect is super important. So I would say really communication is a key, and respect for each other in this diverse organization. But thank you for the question. I think that's one of the most important questions that can be asked in this space.
I agree. Thoroughly good discussion. We have Luxie from Imperial. She's an engineer training up, does a lot of work in sensing technology. Luxie, do you have a question?
Hi, Joanna. Thank you for a remarkable presentation. I actually
Thank you.
don't come from a background of data science or healthcare. I'm from a background of engineering, but it's very helpful to me as well. So I have a question, maybe from like an outsider point of view. So obviously you have worked with a lot of hospitals, and when you communicate with them, so what is their willingness to adopt such techniques? Because they will actually probably they will disrupt their internal structure, traditional internal structures. And how can hospitals make their patients trust these kind of technology?
Thank you, Lexi. I think it's very important to think about it upfront and have those conversations, because as with everything, same with the healthcare, systems, this comes at cost. As you say, we have to integrate with hospital systems. We have to usually adjust their internal pathways and internal processes to be able to work with another solution. And if you think about it, often what happens is that this is a lot of burden on those institutions, because we are tech companies. Our main focus is bringing the technology and solving problems, right? But for hospitals, the main intent is actually saving people, right? Making them healthier. It's not integrating another healthcare system into the mix. So being respectful is definitely one important aspect. And also talking about their longer term strategy and making sure that what we can help with is not just a point solution, because then what they end up with is hundreds of those pointed solutions that are extremely hard to keep on top of, make sure that the clinicians actually understand the use case of each of them and actually the overhead that each of those systems onboarding adds to their workflow. But as they think about, 5-10 years into the future, where would they want to be? What kind of improvements they would want to have and see in the system? How can we actually remove that burden? For example, by bringing their healthcare record to one coherent picture, instead of accessing multiple records with multiple different systems. And then, another important aspect is like how we can help in the process of bringing that technology in a safe way into their environments. So it's not only, this is the pack of software that you take and you start using, but how we make sure from every single aspect, from the data security in the system, from the onboarding of the clinicians, so they actually can make full use of it in the patient treatment, but actually to the last aspect that you said, from the patient point of view, how we make sure that the patient is in the conversation, that the patient understands what is happening with their data, with their treatment, as well as with the overall system and how their data can be used. To give a slightly maybe disconnected example, but one that I think visualizes well how including people in the decision making can really build better standards. As you think about medical research, if you ask people, is it okay for you to just take your data and share with anyone who wants to do research? Probably majority will have concerns. Because healthcare data is one of the most sensitive data we have. But if you were to support the discovery of treatment for the disease that you or someone close to you may have, through sharing of that data in a safe and anonymous way, most of people would actually be for that, right? And then the question is how we make sure that people understand what the anonymity of the data means, how we ensure that they trust all of the players in the system to do the right thing. So for example, for the institutions to share the data that is anonymized, for the receivers to actually treat the data with all the regulatory respect that is required, and how we bring all those aspects together in order to be able to change the system.
Absolutely. Okay, so we're going to have to close this session. I know there's lots more questions, but we're just running slightly out of time, and I know that you've got another talk to go to. So thanks very much.
Thank you for having me. It was a pleasure.
Stay in touch. All the
Have
best.
a good day. Bye-bye.
Okay. We're going to move on to our next speaker. We're just going to do a quick test. Adriana, can you hear us?
Yes.
Perfect.
Yes, Neil, can you hear me?
We can hear you and we can now see you. Yes.
Yes, thank you.
Thanks very much. I realize, again, everyone is insanely busy.
Yeah.
Okay, so we're going to move on to our next speaker. So we've heard a lot so far about devices, new technologies from industry and academia. And now we've got the World Health Organization, the lead in terms of medical devices, and looking into producing global impact on a massive scale. And I think one thing that we often need to think about, and it has been touched on, but not so much, is looking at devices and technology in developing nations and low-income settings. So we have the lead of medical devices from the World Health Organization joining us. So it's an absolute pleasure to introduce Adriana Velazquez Berumen. So looking forward to your presentation.
Thank you very much, Neil, and thank you for inviting me to your meeting. And thank you for accepting that I changed my schedule because we've been running from one meeting to other. So I have my presentation here. So let me share my screens and be able to share with you. So just give me 1 second.
No problem.
Let me just share screen. And then please let me know if you are you looking at it?
Yeah.
Perfect. Okay, thank you, Neil. So I'll go quickly through it and then you stop me if I spend more time than what I should, and to leave some time for questions too.
Absolutely.
So I'm talking about the two sides, the clinician engineer and the clinical engineer, because I think they are totally interactive, actually. Let me see. Okay, so we are engineers or clinicians, and one supports many. So we interact in the healthcare sector together using the technology for the well-being of patients. We have many challenges, huge challenges. One of them is, for example, patient safety. How can we ensure that medical devices would improve patient safety? So it is both our works as a clinician on sides and engineers on other sides. How can we do it better? How can we ensure patient safety? But we also need to support those in the front lines, wherever they are. We also need to have appropriate the use of the devices for emergency and crisis. And well, this year has not been the big difference, although we started with Ebola, but we have earthquakes, and we have having to make decisions with different kind of patients in different parts of the world in different settings. And of course, if we want to increase the availability of global surgery, for example, better diagnostics, then we need the technology to be there for clinicians, healthcare workers, and the work as the technology can help us. As you all know, we have the Sustainable Development Goals, and the Sustainable Development Goal number 3 is about good health and well-being. But exactly the logo of it is an EKG. So that means how the technology really brings health to patients globally, worldwide. And just below of it, it is this about industry, innovation, infrastructure. And we really need innovation and infrastructure and technology to make sure to deliver good health and well-being globally. When we talk about the Sustainable Development Goals, there is the number 3 that is about this one, good health and well-being. But if you start looking into these images, it doesn't matter which of the areas we choose, there's always technology involved. Even from maternal mortality, you need a scale, you need a fetal monitoring, you need for newborn and child mortality, you need for communicable diseases. For non-communicable diseases, then you go into glucometers and you go into cardiovascular, stroke, diabetes. etc., etc. You go to road traffic injuries, you need all kinds of technologies, even X-rays or maybe prostheses, and so, etc., etc., etc. So the Sustainable Development Goal number 3 is about universal health coverage. So the main goal is to cover population with good interventions at a fair cost. How can we achieve that? Well, with the best human resources, with information, with medical equipment, medical devices, with the drugs and medicines, with the facilities and the information that brings us all together. So once all the things need to be interacting at the same time. So healthcare workers and technology have to be working at the same time on the level of information. When we talk about medical devices, we have the full scope, and we have all the medical equipment that has embedded software in it. We have also the medical software by itself. We have all the single-use medical devices, and now something that is becoming very famous is personal protective equipment. But then we also have all the surgical instruments. We have all the implantable devices that we can maybe even program them from the outside. And then we have all the in vitro diagnostics. And most of this equipment work outside the patient, but now they are being used by patients, and they need a third person, a doctor, a nurse, or a technician to use them. So the sequence to ensure access to these appropriate health technologies is 3 layers. The first one is the technology regulation. So you have a product, somebody has to approve it, that it is safe and performance of a good quality. And then you have to do the selection, which technologies should you use that would provide clinical effectiveness. But then we also go into the issues about the ethics, the social issues, the organizational issues, budget, training, and then we go to health technology management. That's really about the use. So once we get the supply, how do you select, use, and train? And using these same 3 colors, we have these other slides, slides, and all the material that we have in WHO has these colors, just to make sure that we get it. Everything in red is about industry and academics, so that the innovation should be based on the needs. In the health technology assessment, that is how do we select priority and essential list of medical devices, for example, for reimbursement, for procurement that will be paid by the health systems. The regulatory part on part of the approved medical devices for marketing in countries. And then on the management side, how do we procure, install, train, maintenance, but ensure the safe use and the clinical effectiveness of these technologies. And finally, the decommissioning and replacement. We have been developing many books in WHO, and this is about the human resources for medical devices. And it is specifically talking about the role of biomedical engineers. And then we talk about the clinical engineers, but it's really what are the biomedical engineers, what are they doing, and the roles for engineers, and then having from the innovation, the regulation, the use, etc. So this is something that would be very complementary. And of course, it touches about the role of the multidisciplinary. So both clinician engineers and clinical engineers are essential to supporting positive health outcomes. So we cannot do without the others. So technology is really invading all our systems, from very basic one, complex, but for a long time, or even more complex now with the IT systems going. So what we are doing in WHO is we're working with other professionals, and we have, for example, we work very closely with the Biomedical Laboratory Science, with the Federation of Ultrasound in Medicine and Biology, with the radiologists, radiographers, hospital engineers, but also with the health technology assessment and the industry sector, like the Global Diagnostic Imaging or Medical Technology Alliance. But then we are also searching for more expertise, and so we have collaborating centers in Brazil, in Mexico, in Switzerland, in Canada, in Cuba, China, etc. And these are centers where we have a collaboration, and they are supporting WHO in all the work that we have to do. something that goes beyond the area of the medical devices, and that's always an issue of saying who is responsible of what, is if we have what is the digital health. So anything that goes into the telemedicine, because it has a medical devices component, then it sits in the medical device. And then we have the interaction between the electronic health record in the data telemanagement, for example, hospital information systems or electronic health record. But when we go here into surveillance of disaster, emergencies, pandemics, or everything about teleeducation, that has no medical devices embedded in it. So these two are like complementary, but they do not go through the regulatory part for the medical devices. So if we have difference and commonalities between digital health and medical devices, what we have is all the analog medical devices. It's basically all the instruments. And then we have all the digital medical devices in hospitals and patients, as personalized medicine, computer-aided diagnostics, software as medical device. So all of them, they do have a medical device component into the IT system. And then we have these ones that were exactly the ones that I mentioned here about teleeducational surveillance with no clinical or patient interface. That is more a general IT perspective, but without the medical devices embedded in it. So when we talk about medical devices, we try to find out which country is assessing medical devices and how is the decision being taken. So we are updating the Global Atlas of Medical Devices right now in December 2020. And these are if you go to the Global Atlas, you will find exactly where are the list of available list of medical devices that are approved or not for different countries for procurement or reimbursement or UHC coverage or even for emergencies. No? But what we have seen there is that most of these medical devices are evaluated for their safety and their clinical effectiveness. And that's all the aspects that is done. But what about the economical consideration? What about the budget impact? What about the organizational impact? What about the acceptability to healthcare providers? So physicians, nurses, technicians, acceptability to patients. So we really need to cover all this area that has been uncovered. The ethical issues are a huge impact and we're not considering them. So all these aspects need to be considered for medical devices. And this was a survey that we did in 2015. The 2020 is running right now. So we will be able to show you if there's any other updates on that. In the WHO's side, what we're doing is we're trying to define what medical devices are requested for which interventions to cover which diseases. So the first book we did was to define the priority medical devices by interventions and levels of care for reproductive, maternal, newborn, and childcare, because WHO has guidance on that. The second book that we did is the priority medical devices for cancer management, which was a very complicated book to do due to the diversity of the technologies. Then we started the selection and use of essential in vitro diagnostics, and those had to be linked directly with the diagnostics for the patient. And right now we were working in 2020 on the diagnostics for priority medical devices for cardiovascular, stroke, and diabetes. And we were working on that when COVID hit. And then, so this book was put a little bit aside, and now we're going back to it, and we have to finish it this year anyway. And these are some of the publications that are mostly related to the work of the clinicians, engineers, that I think would be interesting for all of you to read it, or at least to put it into your scope of work, because it is the regulatory framework for medical devices that has a lot about AI, the human resources for medical devices, then all these books that we have about priority medical devices, and this one that is about the compendium of innovative technologies. So these innovative technologies, we make a call every 2 years about innovative technologies. And for example, just 2 hours ago, we were in a panel of experts, the respiratory therapy, to decide which other technologies we should add into the compendium for WHO. But I take the example of cancer, for example. And in the cancer one, we have about 1,000 medical devices. And those are, which are the devices that would go to be used for prevention, which ones for diagnostic and screening, which ones for treatment or palliative care, which ones for monitoring and end of life. And if you see this, of course, when you enter each of these ones, you enter to pathology, you find a range of maybe 50 technologies. You enter to endoscopy, we have a teleendoscopy, video endoscopies, etc. You go into nuclear medicine, etc. So each of these is a wide range of technologies. And the idea is, how can the healthcare workers, how can the doctors be more trained on each of these technologies to have a better outcomes for patients? So it's not the engineer that prepares the machine, but really the doctors are the healthcare workers are finally the users of them. So how to have the best use of all these technologies. On the area of the in vitro diagnostics, we started just 2 years ago, and this is because we had a request for WHO to say which were the most important diagnostics that should be there. But then the COVID came, and then we had to stop that work and then shift to, okay, how can we protect healthcare workers? How can we have a better diagnostics, and how can we treat patients the best? So we had a shift on saying, okay, now we are going to define what are the properties of the mask, the properties of the goggles, the in vitro diagnostics, etc. So that is a work that we were doing. So to the list of our priority medical devices, we had 2 new ones. This one that was just published 2 weeks ago, and it's called Priority Medical Devices List for COVID-19 Response and Associated Technical Specifications. And this book on the selection and use of in vitro diagnostics, that will be published in December, maybe 2 or 3 weeks from now, or early January. And we even did the technical specifications for personal protective equipment just a week ago. So for the COVID response, we have these, the priority medical devices. We have the link to the clinical interventions, and these clinical interventions, they're matching the new guidelines for COVID treatment of patients. And we go from primary, secondary, and tertiary care, which interventions have to be for protection, which for diagnostic, which for treatment, and which for rehabilitation and palliation. And because this is a moving target, we call this interim guidance. So if there are more things that are developed or discovered in the next month, then we will be updating these tools over and over. And the technical specifications descriptions are matching those requirements for COVID patients. We had this morning a meeting about computer-aided diagnostics for COVID, so we might be adding that in 2 months' time or 1 month time, so we know. This is the other one that was released 2 weeks ago on priority list for personal protective equipment and their technical specifications. And this involves surgical masks, non-surgical masks, face shields. But right now we're looking into innovative PPEs to see if we can find biodegradable ones, or maybe a combination of PARP and other devices. We, as reading books is becoming like the old way to do things, we are now merging everything into a website to have, and this will be called the MEDEVIS, Medical Device Information System. We expect to release it in the next month. And it includes more, now we are about 2,000 types of medical devices. So you could click in here and then find all the specifications for the devices and the training for it. Let me just go into the essential diagnostic list that is complementary to the priority medical devices, and that goes into, we divided into which tools are available for community health workers or for specialized settings or hospitals. And we have divided into 2, general diagnostics or specialized diagnostics. So for general, we have serology, microbiology, mycology, parasitology, but then we also have for disease areas, and then we have HIV, tuberculosis, malaria, etc. But we added ones for cancer and other diseases lately. I'm not going to go through these slides because it is really heavy, but the main idea is that healthcare workers or the industry can make a submission to WHO and then request that a new technology be added to any of these lists. Then we have a strategic advisory group, we review them, we review the evidence, we go through all the information, and then we decide if it is placed in the system or not. No? And well, at the end, we will have all the guidance and everything will be done in an electronic version. As you can see, this is the book, but then this is the electronic version that will be available also quarter 2020. This was supposed to be launched in March, and of course we had to postpone it because now we added the COVID test. And the idea is that you can go through all the tests and then be able to have the information about why it was added and where is the evidence and the training guidelines. And the idea is that all these tools are developed by WHO, are given to the countries will compare it with their local needs, epidemiology, resources, and setting, and they will decide where they will place these technologies and they will train their health workers for them. Due to the COVID situation, of course, now we were requested to add things, and you can find them under country and technical guidance. You will find all the latest guidance on medical devices and PPE, and almost every month we update something. There was a new release just yesterday night about the use of masks, for example. So we are working constantly to change this information. Things that used to take like 1 year, now we're doing it like in days, no? For example, there's another one on the screening and diagnostic steps for patients. We start the screening with a pulse oximeter, then we go to PCRs and RDTs, as you know. But then we also have the ultrasound, the X-ray, and the CT scanner of 64 slices. And this we just released in June. We released the list 2 weeks ago, and now we had a meeting today, this morning, on how to use the computer-aided diagnostics to support this work. And maybe in a month's time, we would release an update for this one. Everything is published in the COVID website. You can find the emergency supply chain, the list of priority diseases, and then all these guidance will go into the supply chain because we now have to provide technologies for 120 countries. So it's going there. And this is the chain for the innovation. So we did a call for innovative technologies for COVID and other related diseases. We go through an expert panel. They present, they do a pitch presentation, we do a voting, if approved, we put it into the compendium, and if approved and really urgent to procure it, then we go to the emergency supply and we procure it. We are doing also research on coronavirus disease, as you all know, but another thing that's very important, we're going also to the technology access pool. That means technologies that we think that they are good to be locally produced or technology transfer. Then we're going through that part. So that is the research and development and technology access pool. In conclusion, WHO has methodologies to select essential and priority health products. They're all based on evidence and expert groups to make the decisions. The objective is that these lists serve as a reference for member states so that they can be adapted and adopted globally. And the idea is that they will support universal health coverage, emergencies, and well-being for the population. And this, I think it is very important. It's not only the technical knowledge, we need passion for all of us. We need transparency, how things are decided, how we bring the evidence. We all have to work very hard, but most of all, we have to collaborate. So when Neil invited me to this meeting, I said, yes, I'm willing to come because if we don't collaborate, we cannot achieve these things together. So that's my presentation. Thank you very much.
Amazing. Thank you so much, Adriana. I fully agree. The impact that you're creating from the WHO in terms of devices, diagnostics, and healthcare technologies. I think everyone, part of your team and yourself, completely leading the way. So we're going to start off with the questions. Lady Catherine's going to lead with Faisal. So Lady Catherine's based in the US, in Cleveland, and Faisal's coming in from Dubai.
Good morning, Adriana. Thank you very much for such a nice presentation. I think I'd like to particularly state that sounds like, I mean, COVID definitely has been a huge challenge for everybody. And it's so nice to see how resilient the world has been towards it, although it has been a massive change in how we have to live. So it's very good to see how the WHO has also somehow become very flexible and resilient in that regard. Yet at the same time, not forgetting about the things that are still going on, because there are other medical issues that are also affecting populations. One of the big questions that I've always had is how to prioritize and how to determine which tools should be developed and how to guarantee that all those tools are to somehow a degree be used by everybody in the world. Because one of the things that I have seen particularly and personally is that at least in certain countries of the world, we have such the best technology and we can apply it here. But there are other areas in the world and we create so many guidelines that apply for this amount of the population, whereas the population is so big and there are other areas that we wish that that technology could reach there, but sometimes that's a little bit challenging. So from the WHO perspective, how can we best tackle that difference between both worlds and how to make sure that the technology reaches everybody?
Thank you. Yes, thank you for your question. And actually, that is why we call them priority medical devices or essential in vitro diagnostics. So even though we have a huge list, we have to select which ones are the most important and which ones will make a change. So for example, when you go to cancer, we were talking radiotherapy, and if you see the list, you will find both the cobalt unit and the linear accelerator and the brachytherapy. So you will find the three sets. And then we said, depending on your resources, then maybe some countries could not go further than the cobalt unit. But if you realize, it is very important because there are 31 countries that have no radiotherapy equipment at all, means zero. So people have to travel somewhere to get the radiotherapy done. So when we talk about that, that's when we really find out so huge disparities in the world. So the main idea from WHO is to just, for example, not just supporting the donation of radiotherapy equipment, but also supporting pathology and telepathology. If you have telepathology, even if you don't have experts in the country, then still you can get the slices, the pathology done, and then send it elsewhere so that somebody can advise you, yes, this patient needs blah, blah, blah. No? So we're looking into that to maybe to make technology available and more affordable where it is needed, but also not just getting the big donations of the big machines, but also have the whole process of getting a good diagnostics. And that's why I put the image of the cancer, because without a good diagnostics, it doesn't matter the rest. No? So that is the idea, to improve the diagnostics, the early diagnostics, so that then we can improve the early treatment and would lead to less costly interventions. But it's a huge task. It's a never ending. And well, yeah, that's why I said we need passion and collaboration. So we'll be glad to work with you.
Absolutely. Also because there are certain diseases that attack certain parts of the world and not others.
Well, we have the malarias, the HIVs, the tuberculosis. We're working very, very hard on the tuberculosis. It hits many, and it might not be important for other parts of the world. So that's why we have to look for everybody, and especially the poorest and the sickest. Those have the super priority in WHO.
Well, that's very reassuring. It makes me very happy. Basum Mahin, she has a question for you. She's asking, can you elaborate more on the technology transfer and capacity building portion?
Yeah. What we do is that we have actually some publications on the website that is called Local Production Technology Transfer. We did that study in 2014, and then 2015, we were in 4 countries, Tanzania, Nigeria, Ethiopia, South Africa. And then we were there, and then we said, okay, what are the huge needed? No? And then what is the capacity that can be done here, and what can we develop locally? And that is where we're doing technology transfer. And right now, there's a huge area for technology transfer for example, the mask production. So what are the characteristics that the clothing or the polyethylene or the polypropylene materials have to have in order to have that the breathing and the filtering that's needed to comply with standards so that it can be locally produced. So we're working on that. It is called Technology Access Partnership. I can put it in the chat so that the interested persons can work. The idea is to get manufacturers to give out their blueprints so that somebody else can produce. And manufacturers are willing to do it. So we're very happy to see that happening. I hope that clarifies.
Absolutely. Thank you. And we have another question from the audience. Medical healthcare workers and patient acceptance is very important. It's a very important part of the process. What can be done in order to overcome this resistance?
Yeah, thank you. That is important because actually what happens is that technologies are invented and they are used, and sometimes they're even donated. But if it is not acceptable to the user or to the healthcare worker, not even if it is given for free, you will not take it. I just have two very quick examples and you might think very not big, and these are very simple technologies. One is a hearing aid that is a box like this size, and then you hang it here, and and you have the hearing aids. People didn't want to use it because everybody would notice that they were deaf, no? So even if you give it for free, they will not use it. Another one that is huge is the female condom. So women have to have control for their reproduction, but still they are not eager to use the female condom because it is very difficult to use. It is not easy. And so women, even if they have it, they don't like to use it, no? So there are many technologies, and I'm just starting from very simple ones, and then you can go all the way up to complicated technologies that if the healthcare worker doesn't feel that this is something that they can use, or the patient, it doesn't matter. It doesn't matter if you give them for free, they will not use it. So acceptability to patients and to healthcare workers should be like a number one. And the other thing is that we don't have standardized methodology. And I'll just tell you, a ventilator, no? Every brand of ventilator has different settings in a different place in a different way. So if you learned one and they donate you a second one and a third one and the fourth one, each of them has a different setting. Each of them has a different sequence. You go to, so that becomes really, and sometimes, you know, mistakes number one are the infusion pumps. And why is it? Because of the sequence of the programming. So they're very simple devices that we need to do much more for acceptance of the healthcare worker to avoid the mistakes.
Right, yeah. Right. No, well said, Ms. Adriana. And I think sometimes just going back to those basics of what exactly is causing our problem could cause a bigger solution at hand rather than just infusing technology without thinking what could be the resources that we can use ready in our hands. I agree with you. And I think we have another question coming in, which is along the lines of machine learning and artificial intelligence. They can help as great equalizers in the future. So do you personally see a useful application for health data outcomes within the public domain in terms of global accessibility in the future? In terms of, well, overall global scale, both in bidirectional and dynamic interface for learning?
Yes, absolutely. So we are working on that in WHO. We have the regulation is software as medical device, but what we really want to do is how can you use AI to really improve the training of patients, the training of healthcare workers, and the availability of information. We have to take a lot of concerns, just as the previous speaker was talking about the confidentiality of information, of data. But if it's done in the right way, we can really save patients. We can really empower healthcare workers to make better decisions if we have that support. So we just have to do it in the ethical way and a protected environment, no? So if that is done in the right way, the success could be marvelous. And we really should not stop using technology, but just always keeping in mind the ethical part and the human part and the outcomes of the patient. It is the patient that matters the most. It is not the technology. So that is my logo for everything. And by the way, I have a white pen. I don't know if you can see it, but it's a white pen. And my white pen, every time I go to meetings, but of course I'm not with you today, but I have it here because it is not the technology that matters. So the white pen is just to remember us, it is the patient that matters the most. So how can we use the best technology to meet the patient's expectations and the safety of the patient and the patient's outcome?
Absolutely. That's a great debate. We've got Luxie from Imperial. Have you got any questions, Luxie? Hopefully she can hear us.
Yeah, thank you very much, Adriana. It's a very insightful talk for me. I work with, I'm a PhD student and I'm working with sensors, so basically in vitro diagnostic sensor. And for my work, the main aim for my work is to fabricate sensors in point of care settings. So my question is, from your perspective, so could you please tell me what would be like the future direction of point of care diagnostic sensors, and like how can they help, for example, third world developing countries?
Thank you, Luxie. That is a very good question, because actually what we want to do is empower healthcare workers and empower the patients at the very beginning, at the community level, so that people don't have to go to high-level hospitals and specialized hospitals to be tested. So if you have a point of care that really can tell you this is a virus or a bacteria in the place, so then you will get a lot of less problems of antimicrobial resistance, for example. But a nurse or a doctor should be able to do it at a healthcare center. It doesn't matter where. It can be in the middle of the mountain, in the middle of an island, anywhere. So having good technology to have a good diagnostic in the place where the community lives, that is the best way, because many patients cannot make it to a district hospital or complicated hospital. And when they are really sick, that's when they go, and maybe you cannot save them anymore, no? So what can we do to save them before? If we diagnose them before, we can treat them before, and then everything will be better, no? It's a better outcome. So yes, the future is really having like essential diagnostics in the point of care at the community level. If we empower those, that would be marvelous, no? So yes, and the idea is, if you look into the EDL, the Essential Diagnostic List, the blue book that I put here, you will see that is all the technologies that now we're happy that they are available at the community level. And we want more, we want many more to be available.
Thank you very much. That's what I've been looking forward to work with, like after I graduate, because I'm really looking forward to working with doctors and like organizations such as World Health Organization, so I can use my knowledge in sensing and like in engineering, and to integrate these people from different backgrounds and to do the best for example, developing economies. Thank you very much.
Okay, no, you're welcome. And yes, keep on working. We need a scientist that brings the technology to the community and make sure that patients are treated.
Yeah, thank you very much.
And treated. You're welcome.
These are actually fantastic points again, Ms. Adriana, and I think it makes me wonder about how communities and resource allocation comes into play. Because we're looking at managing such large scale problems. How do you prioritize infrastructural setup, or which crisis is more at hand for you to work on? Just curious to see from your side of things.
Well, something that is absolutely indispensable is to have electricity, to have water. That's indispensable, and to have now Wi-Fi access. If we have those three elements, we can do a lot of things. And right now we are in searching for oxygen sources too. So if we can have those things available in the setting, those are like basic things that need to be there, and then many other things can happen, because we're looking into solar powered technologies, but it is still not as efficient as we need. We have now, for example, oxygen concentrators that are driven by solar power, but then you will need also for the pulse oximeter, you will also need it for the surgery, you will also need it for pregnant woman and ultrasounds. We're looking into small size, like really iPhone size ultrasounds, which is really good. So, and have batteries in it. So that is where we're looking. Technology that will be easier to use, faster to use, more reliable, more affordable, and that will have like self-contained, so that you require less gadgets from the outside to make it work.
Right.
I don't know if that was your
Yes,
question.
yes. I mean, we're looking at how technology is being implemented, and at the same time, like you mentioned, projects on tuberculosis, malaria. I mean, looking at so many of these health concerns and problems, how do you prioritize which one is more of an attention or action-seeking topic for now?
Well, Faisal, something that happens is, for example, HIV, TB, and malaria have a lot of resources, and a lot of organizations are putting money into that. But you have the rare and orphan diseases. You have, for example, sickle cell. Sickle cell, many, it is like a type of anemia. I don't know if you know sickle cell, but it's a type of anemia, and patients die and have a very, not a good kind of quality of life. And if this is detected early, and we were just very happy to know that there are new to, and just about the other person that just asked me the question, there are new 2 point-of-care technologies just available this year, last year and this year, for point-of-care sickle cell. No, so these are things that maybe for others is not as important, but they are super important. So let's look into those orphan diseases that nobody's putting money on that, but still the people are dying about it, and they are not in the high visible spectrum of the donors, and we need to get them also the attention there. So that's why we have these expert groups trying to bring people from all settings, and trying to define what are the priorities really for each of the areas of the world.
Yeah, this is absolutely inspiring, and I think that's very much along the same lines of what we look at as part of the Clinician Engineer Hub, where it's about looking at all the communities that require attention and need, and even if it might not be the most popular topic of concern and might just be the most niche of what we're looking at, like you mentioned, all of them deserve attention. And through such collaborations, we'd be hopefully having more initiatives coming along these topics. So thanks a lot, Ms. Adriana. It was our immense pleasure to actually have you on board with us as part of this discussion. Anything from Dr. Neil or Dr. Lady Catherine's side as a closing note?
Thanks, Faisal. No, it's just to second what Faisal was saying. Thank you, first of all, for spending the time, because I appreciate how busy you are in Geneva.
Yeah.
And the discussion was immense, and all the detail and work that you're doing. So we're very excited about the future. So thanks once again, Adriana. We'll be in touch.
Thank you very much. Thank you. Bye-bye.
Bye. Take care. Okay, everyone. So we're going to take a quick break. Our final talk is at 1800 UK GMT. So have something to eat and drink, as I always say, and we'll see you for the final talk at 1800. All the best.
Yes, sir.
Okay. So hi, everyone. Some unfortunate news. Professor Anima is unwell at the moment, so we won't be able to close with her talk. However, she has promised us that she will speak at a later date, so definitely watch this space. It's been a fantastic 3 days. As I've always said, the best engineers and healthcare physicians, surgeons, people from industry coming to you live completely free of charge. Obviously, this would be impossible without my team. So I want to thank my founders, Ali Edson, Mads Bergholt, also all the strategy leads of the Clinician Engineer Hub, who have really promoted and done wonders for this. So Faisal Nawaz, from Dubai. We've got Catherine, direct from the United States in Cleveland. Chloe and Maria from London. Laura and Luxie, also from London. And all the social media ambassadors who I have seen have been live tweeting over these 3 days with all the best points you can imagine. And I think having spoken to Faisal, we've really hit a large proportion of people in the millions. So that's very interesting. So I'll provide that data shortly. Faisal, do you have anything you'd like to say?
I'm just absolutely, I think, grateful and happy at the same time, seeing the number of questions, engagement, both on Zoom and social media that came forward, simply because of the time and efforts of people who offered to donate some of their wisdom and insights in the field of clinician engineering. So thank you to each of our speakers. Thank you to our attendees. And some of them have been very consistent with attending, and I've been noticing that. And again, we will be having certificates given to all of those who've attended actively over these 3 days. So watch out for your emails. And once again, I think our social media ambassadors team has done excellent in terms of promoting some of these talks. It was as good as watching the talk on social media, if that makes any sense. So really happy with everything. And then thank you to hosts, co-hosts, and our founders of the Clinician Engineer Hub.
Absolutely. Lady Catherine?
Yeah, well, I'd like to thank those who are online who took some time and who are thinking about this hybrid of clinician engineers to keep pushing it forward. It's just also it's a tool for you primarily, so keep it up. And thank you for the Clinician Engineering Hub. Thank you to Neil and thank you to Faisal. Thank you to the founders and everybody who makes this possible, as well as our speakers who, as you both said, they have dedicated part of the time so we can push forward with the youth, because that's where the future stands. So let's keep it up.
Absolutely. And I think it's a really fantastic end to December 2020, despite what is going on an international scale. So I hope everyone stays well. We have lots of exciting events happening in 2021. So we're going to hold our first hackathon in March. There'll be more conference events and really exciting opportunities. So we're going to put out more research opportunities and internships for those that are interested. Okay, so I'll close it there. And as you can see, I'm smiling. We survived. All the best, everyone. Take care. Bye-bye.